Something happened on October 13th that will either be remembered as a clever hoax or the moment our story turned. An interstellar visitor, the object we call 3I Atlas, allegedly flashed light in a pattern that should not occur by accident. 5, 8, 13. The sequence of growth that echoes through shells, storms, and galaxies. It happened while key observatories went quiet and while the object slipped behind the sun where we could not look. So is this a coincidence stacked on coincidence, or choreography? Stay with me, tap like and subscribe now, because the next minutes decide how we think about all of it. Imagine you are trying to be seen and not seen at the same time. You do something headline-worthy, then step into the brightest glare in the solar system, a place where terrestrial telescopes are effectively blind. That is the paradox we walked into on October 13th. The mathematical claim is simple enough for anyone to repeat, yet hard enough to verify that even professionals cannot settle it until the geometry changes. In the gap between those facts, the story blooms, and that is why we begin with patience, not panic. First, the sequence. 5, 8, 13. People attach meaning to those numbers because they sit on the Fibonacci stairs, where each step is the sum of the two before it. When ratios between steps converge, we get the golden number that artists and engineers love to chase. Nature uses this ladder because it packs things efficiently, petals and seeds and storms finding balance without trying. If a real object pulsed with those counts, it would feel like a hand tapping a universal drum. But feeling is not evidence. We have to ask how a real optical signal would be detected, logged, and reproduced by independent groups. Second, the stage. 3I Atlas reached the part of its path where the sun itself becomes a curtain. From Earth, even our best optics drown there. The Solar Dynamics Observatory, the crown jewel for watching solar behavior, announced maintenance. The high-resolution camera aboard the Mars Reconnaissance Orbiter experienced issues earlier in the month. Whether those outages are mundane or meaningful is less important than the effect. They slow verification. They turn a yes or no question into a long pause filled with speculation, and pauses invite stories. So, we will do what good investigators do. We will separate what was seen from what was said about what was seen. An honest signal would be a time-stamped sequence recorded by more than one instrument, ideally in different bands of light, with metadata about exposure, pointing, and calibration. It would be accompanied by a short method, not a manifesto. It would be shared in a way that lets other teams try to catch the same drumbeat. We have claims. We do not yet have that package. That is not a verdict. It is a threshold. Why do numbers land so hard on our minds? Because numbers feel clean when the world is messy. A simple ladder whispering through an interstellar visitor satisfies our love of order. It also bypasses the usual gatekeepers. You do not need a physics degree to understand a count to 13. That makes the idea powerful. It also makes it dangerous. We will use the power and manage the danger by asking the same two questions after every headline. How would this be measured? When can we measure it again? Now let us talk timing, because timing is the gasoline here. The claim arrived on the anniversary of a mass-witnessed solar phenomenon at Fatima. Tens of thousands looked up in 1917 and saw something they could not agree on. Some felt miracle. Others proposed atmospheric optics or crowd psychology. What matters for us is not settling Fatima today. What matters is recognizing how anniversaries act like magnets for meaning. If you want a signal to be noticed by everyone, you tether it to a date that already hums. That can be strategy. It can also be the way human memory compresses, chance into fate. There is another clock running that is far less poetic. It is orbital mechanics. For roughly 6 weeks, around late October and November, 3I Atlas sits where Earth cannot get a clean look. That window opens and closes, whether you believe the claim or not. When it closes, the object will emerge back into skies we can study. That is when amateur and professional networks will compare notes, refine the path, and check whether anything about the motion changed in a way that normal outgassing cannot explain. If there was a burn, even a subtle one, the numbers will tell on it. Numbers are stubborn that way. Between now and that reappearance, our work is to map what counts as a test and what counts as theatre. A test looks like a prediction written down before the data arrives. For example, if the outbound speed is lower than the inbound by more than natural processes can justify, then something added a brake. Or, if the spectra show distinctive changes in nickel and cyanide plumes compared to August, that would point to a shift in activity zones. Theatre, by contrast, promises revelations without timestamps and moves the goal whenever the sky refuses to cooperate. You might be asking why we are spending precious minutes on caution when the thrill is right there. because caution is the only way to keep the thrill honest. We can hold two ideas at once. 1. The Fibonacci claim is exciting and feels like a door cracking open. 2. Rigorous follow-up is not optional if we care about truth. That is the contract of this channel. We chase the wild story, but we never give up the boring measurements that make the story worth anything. Here is our plan for the chapter ahead. We will decode the claim in plain language, explore why brains love the pattern, walk through the blackout window in simple geometry, and show how a maneuver at closest approach would be hidden and yet detectable after the fact. We will also stack the earlier oddities around this object, so you can see the cumulative picture without drowning in jargon, and we will keep a running list of checks the global community can make the moment the glare eases. If you stay through that map, you will be able to judge new headlines in seconds. So let us step into the maze with clear eyes. Maybe the pulses were nothing more than noise arranged into meaning by hope. Maybe they were real, a gentle knock using the oldest language we share with the universe. Either way, the truth is patient. The sky remembers what passed through it. Our job is to meet that patience with discipline and curiosity. You are here for that. I am here for that. And together we will decide if this night of Fibonacci was a trick of the light or the first line of a longer message. Start with the simplest version of the story. On October 13th, a handful of observers say that 3i Atlas produced a brief run of optical pulses that could be counted as 5, then 8, then 13. Not brightness slowly rising and falling like a normal comet flare, but discrete beats that seemed intentional. Could a natural object stumble into that rhythm by chance, or is someone trying to get our attention? Before we chase meaning, we need to translate the claim into measurements any careful observer would recognize. A real pulse train has 3 ingredients. You need timing, amplitude, and context. Timing is the spacing between peaks. Amplitude is how much brighter the object gets compared to the local baseline. Context is everything that could fake the same pattern. Thin clouds drifting across a star field can create false steps. Wind shake on a long lens can modulate light curves. Auto exposure on a consumer camera can pump brightness in a way that looks like heartbeat. So a trustworthy detection does not just show a jagged line and shout pattern. It provides raw timestamps, exposure settings, pointing coordinates, and the exact processing steps used to extract the signal from noise. Imagine you are the second lab trying to replicate it. What would you ask for? First, a time window and a reference clock. If I point a telescope at the same patch of sky and record the same minutes, can I see the same steps? Second, a control star near the comet recorded with the same gear. If both the comet and the control star show the same rhythm, the pattern is in the atmosphere or the camera, not the object. Third, a description of the filter used. A neutral color filter might show one behavior, an ion-line filter might show another. Without those pieces, we are arguing about feelings, not physics. Now the numbers that hook the public, 5, 8, 13, are stepping stones in the famous Fibonacci sequence, where each number equals the sum of the two before it. When you divide one step by the next, the ratio approaches the golden number used to describe spirals and efficient packing in nature. It is a gorgeous story beat. It is also a textbook case of why we separate resonance from rigor. If a real intelligence wanted to announce itself without ambiguity, it could send a longer sequence with clean spacing and a repeat. It could run 1, 1, 2, 3, 5, 8, 13, and then start again. It could vary color or polarization in the same count to cross-check the timing. So, one of our first tests is blunt. Was there a repeat? If not, we are looking at a single burst that might be significant but might also be chance. How would a comet produce pulses at all? There are natural mechanisms. Jets on a rotating nucleus can swing in and out of view, causing brightness steps. Fragment shedding can create short spikes as sunlight hits fresh surface. Dust clumps drifting across the inner coma can momentarily alter how light scatters toward us. None of those care about Fibonacci. They care about geometry and sunlight. But given a noisy environment and our very human love of patterns, a few irregular steps can look like a code if we stare hard enough. The antidote is boring and reliable. We ask whether the intervals match a rotating lighthouse and whether the next night shows the same cadence. What about instruments that could have helped? The Solar Dynamics Observatory reads the sun in multiple bands and can catch transients near the limb, but it is not built to track faint objects against the glare. The Mars Reconnaissance Orbiter camera, at 3i Atlas distances, could have sampled large-scale features if pointed and processed carefully. Ground-based telescopes with fast photometry can do the timing work if the object is clear of the sunday. During the blackout window, the easiest verifiers are off the table. That is why the claim lands now instead of later. It forces a choice. Do we anchor to an attractive story, or do we hold position until the sky lets us test it? Let us talk about the messenger. The researcher who popularized the analysis has a long record of connecting mathematics, sacred geometry, and orbital coincidences. Some of his earlier ideas looked outlandish and later picked up partial support from unrelated data. Others never landed. That is exactly the kind of mixed portfolio that divides audiences. Some hear pioneer, others hear pattern chaser. Our approach is simpler. We evaluate the packet, not the personality. Does the evidence include times, camera parameters, and a path for independent replication? If yes, we engage. If no, we park it in the maybe pile and keep moving. There is another wrinkle that sounds technical but matters for everyday judgment. Compression and auto-enhancement can invent a beat. Many modern cameras smooth and sharpen video on the fly. Smartphone night mode stack frames and normalize brightness. Social media uploads add another layer of compression that can create apparent steps when the algorithm quantizes light levels to save bandwidth. A convincing detection therefore prefers raw or lossless data, or at least shows a comparison between raw and processed frames. If the pulses shrink or vanish in the raw set, the pattern is in the pipeline, not in space. So what would a strong confirmation look like in the real world? Two independent teams, ideally on different continents, capturing the same count within the same minute. A second pass an hour later, showing either the same spacing or a rotation-consistent shift. A report that includes the control stars and the exact code used to compute the light curve. Even better, a color split that shows the pulses stronger in a specific emission line, which would tie the rhythm to a chemical jet rather than a camera artifact. That is not perfection. That is just enough to move the conversation from thrilling rumor to testable signal. Could this still be real, even without the perfect packet? Yes, in the sense that absence of evidence during a solar blind spot does not cancel reality. But until the geometry improves, the honest lane is clear. We treat the Fibonacci story as a prompt, not a proof. It tells us what to look for when the object reappears. Repeated steps with stable timing, cross filters that confirm a physical source, brightness changes that correlate with the known rotation period rather than with atmospheric flicker. The cosmos will either cooperate or it will not. Here is the promise we make to each other as we keep going. We will not be cynical and we will not be credulous. We will hold the door open for wonder while we ask dull questions about clocks and clouds. If the pulses happened, they will leave fingerprints we can find again. If they did not, the sky will be quiet no matter how loudly the internet shouts. Either way, we will learn something useful about how stories spread and how signals survive. That is a win in a universe that rarely hands out neat answers on demand. Stand with me on a dark hill and picture the solar system like a stage. The sun is the spotlight so bright it drowns everything near it. When an object passes between our line of sight and that light, even great telescopes lose contrast. Cameras saturate, sensors clip. The background becomes a flood of photons that washes subtle signals away. That is not a conspiracy. That is optics. It is also the cleanest hiding place in the neighborhood. 3I Atlas crossed into that glare near the end of October. From Earth's point of view, the object slid behind the sun, not behind in distance, but behind in angle. A small change in angle can turn a visible target into a ghost, because our view is a narrow corridor and the sun fills it with noise. Think of trying to see a firefly held up in front of a car headlight. The firefly is still there. Your eyes cannot separate it from the blaze. Telescopes have the same problem. Their sensors are precise but not magical. Scattered light inside the optics creates a hazy veil. Diffraction throws bright spikes. Saturated pixels bleed into neighbors. The signal-to-noise ratio collapses, and once that ratio drops, confidence drops with it. Geometry is the boss here. As the object moves along its orbit, the angle between Sun, Earth, and 3I Atlas changes day by day. There is a span of weeks when that angle is small enough that sunlight wins every duel. Then the angle grows and the glare eases. That is the opening everyone is waiting for. The blackout is not a single on and off click. It is a curve. The first days feel like a heavy curtain. Later days feel like a thin mist. By early December, the mist lifts and real measurements become possible again. Why did a few outages make this feel worse? Because spacecraft that normally help with messy geometry took their own pauses. Solar Dynamics Observatory performs routine maintenance. Routine is normal, but the timing was rough. The high-resolution camera on the Mars Reconnaissance Orbiter had known issues. None of that proves anything dramatic. It does remove options. With Earth blinded by glare, any extra set of eyes helps. Fewer eyes means slower verification. Slow. Verification fuels speculation. Speculation feeds on itself until the sky speaks again. There is good news. Not every vantage point is equal, which means not every craft is blind when Earth is. A spacecraft far from our planet sees a different angle. A probe trailing Earth or leading Earth may look past the worst of the glare. A craft in solar orbit can watch regions our ground observatories cannot. Even then, design matters. Many instruments are built for specific targets. A camera tuned for bright solar loops is not ideal for a faint interstellar object. A thermal instrument might catch dust and gas differently than an optical imager. The lesson is simple. Coverage is a patchwork. Holes are expected. We plan around them. Walk through a single day in the blackout. Sunrise comes. Observatories open. The object is up in the day sky. Near the Sunday ground-based teams cannot chase it. A few radio instruments can look for plasma signatures. Most sit out. Spacecraft schedules roll on. If a camera is healthy and pointed, a thin stream of data trickles home. If not, we wait. Toward evening, the geometry has not changed enough. The object is still buried in glare. Another day of guessing ends. Multiply that rhythm by 40, and you understand the mood online. People want a daily twist. Physics offers a calendar. Now flip the perspective. Suppose you are an intelligent probe that prefers to move while no one is looking. Where would you time a major change in energy? Deep in the gravity well of the sun, at the exact moment you are behind the light from the point of view of the only planet with billions of curious primates. The Oberth effect rewards you for firing engines when your speed is highest. Perihelion is where speed peaks. The far side is where sight fails. Those two facts overlay like transparencies. Hidden and efficient at the same time. Even a natural comet benefits from physics at perihelion. Gas vents spike, jets flicker, activity rises. A technological craft will simply make the most of the same rule on purpose. Here is what makes this window useful even if you are allergic to speculation. The blackout hands us a before and after experiment. Before perihelion, we have inbound speed, inbound path, and a record of spectral behavior. After the glare, we will have outbound speed, outbound path, and an updated spectrum. If the object behaved like a normal comet, the two sides will match within known models for outgassing and radiation pressure. If the object shed or gained energy in a way those models cannot account for, the mismatch will stick out. We do not need to see a burn to notice that energy went missing or appeared. Trajectories are honest even when engines are shy, so we build a checklist for re-emergence, track the brightness curve night by night, and compare it to the curve predicted by distance and phase. Measure the position with enough precision that tiny accelerations show through the noise. Split the light into bands and look at the nickel and cyanide scale lengths again. Are they the same as August? Are they more compact or more diffuse? Map any jets with lucky imaging and search for repeatable structures that rotate with the nucleus. If the numbers line up with natural behavior, we move one step toward ordinary. If they do not, we move one step toward deliberate. There is a human layer to the blackout that is worth naming. Waiting is hard. Minds fill gaps. Coincidences feel like designs. Outages feel like hands-on levers. You can respect that impulse and still refuse to be rushed. The sky will clear. The geometry will change. When it does, every telescope that can point will point. Amateurs with fast cameras will grab light curves from backyards and rooftops. Professionals will refine orbits and spectra. The internet will fill with plots and animated fits. Somewhere in that flood will be the answer to the only question that matters. Did anything happen in the dark that the math cannot excuse? Until then, the smartest move is to treat the far side as a sealed envelope. We cannot open it early. We can only prepare the tests that make the readout crisp the moment it lands. This is not a passive posture. It is a disciplined one. Curiosity with a ruler, wonder with a clock. When the curtains part, we will know what to look for and how to call it without flinching. Let us be honest about why 5, 8, 13 hits a nerve. Numbers look clean and untouchable. They feel like they live outside the mess of politics and opinion. You hear 5, 8, 13, and your brain whispers pattern, the ladder, where each rung is the sum of the two before it. The ratios between rungs slide toward a golden number that seems to haunt seashells, storms, and spiral galaxies. It is tidy. It is everywhere. It is seductive. Which is exactly why we need to slow down and ask what a real message would look like, and how easily a near miss can fool us. Start with nature. Sunflowers crowd seeds along spirals because that packing wastes the least space. Pinecones wrap scales the same way. The math behind those spirals approaches the golden number because that is how growth steps avoid overlap. No spirit guide needed, just efficiency. So when we see a neat ladder, our brains shout meaning even if a physical mechanism could generate something similar by chance. This is not a flaw, it is a feature. Pattern spotting kept our ancestors alive. Hear 3 beats in the brush and you run. It is wiser to jump at wind than to ignore a predator once. Now, ask what a deliberate optical signal would do if it wanted to be unmistakable. It would not rely on a single pass in poor geometry. It would repeat. It would include a few extra steps so the sequence becomes undeniable. 1 and 1, then 2, 3, 5, 8, 13, 21. It would keep the spacing constant in time units a human clock can test. It might even change color in the same count so that 2 independent channels agree. These tricks are not exotic. They are how humans design beacons for spacecraft. Repeat, cross-check, persist long enough that someone on the wrong side of a cloud can catch the next train. What actually happens in the sky is messier. Comets flicker because jets turn with the nucleus like a lighthouse beam. Dust sheets out in random clumps. Thin clouds pass over a telescope and step the light down and up. Cameras hunt exposure and create their own heartbeat. Any one of those can produce 3 bumps that look like a count. Add the human love of ladders and a short run feels like a message. The fix is dull. Measure the spaces between peaks carefully. See if they fit a rotation period already measured, within uncertainty. Watch again the next night. If the intervals move in lockstep with the known spin, you probably watch sunlight painting across vents. If they do not, be curious. But still, repeat, repeat, repeat. There is another reason numeric stories spread faster than technical plots. They travel well across audiences. You do not need a degree to feel that 5 and 8 and 13 belongs together. You do not need to memorize spectral lines to tell a friend that the universe might have winked in our language. That accessibility is powerful. It is also how hype outruns measurement. Clean digits outrun dirty data. If our goal is to keep wonder without losing rigor, we have to learn a simple rhythm. Feel the pull. Then ask the boring how. How would the signal be encoded? In optical astronomy, that means clear timestamps, precise exposure control, and independent verification. How strong would it need to be? Strong enough that at least 2 differently calibrated instruments agree within their noise. How do we protect ourselves against false beats? We record a nearby star and process it exactly the same way as the target. If the star and the comet pulse together, the pattern lives in the atmosphere or the camera. If the comet pulses alone, you have something to chase. Let us turn the spotlight for a moment onto our own cognition. Confirmation bias is the habit of noticing what matches and forgetting what misses. Your favorite team wins, and you remember the prediction. They lose, and you forget you ever said it. Numbers do this to us gently. If a measured ratio lands near the golden number, we round in our heads. Near becomes exact. Exact becomes profound. We forget the error bars that told us to stay humble. The escape hatch is simple humility turned into a habit. Say the number out loud with its uncertainty, then decide if the match survives the wiggle room. There is also a subtle trap called the many doors problem. If you try enough keys, one will open a lock by accident, test enough ratios, and one will fall close to a famous constant. The cure is to set the test before you look. Write down what would count as a hit. Do not change the rule after you peek. That discipline feels fussy. It is the opposite. It is generous to truth because it gives truth a fair path through the noise. Now, what about the idea that a message wrapped in beloved numbers could be aimed not at scientists but at everyone? That is clever. If you want the world to notice, you do not bury the lead in jargon. You knock with a beat half the planet already recognizes from schoolbooks and art videos. You tether it to a date that hums with meaning. You let the blackout window amplify the mystery. As pure strategy, that would work, which means we must be ready to test a strategy, not just a signal. We should treat the count as a pointer that tells us where to aim our instruments when the glare fades. Here is the most useful promise numbers can make right now. They can generate a forecast. If the pulses meant anything more than noise, we can expect repeatable structure tied either to the rotation period or to a deliberate schedule. We can expect certain emission lines to swell and fade in sync if a jet is doing the rhythm. We can expect timing that makes mechanical sense instead of timing that drifts randomly the way wind and autogain do. Those are tells. We will look for them. You will see them charted in simple plots you can read without a textbook. In the end, numbers that feel like meaning are not the enemy. They are the hook. They pull us into the work of separating music from room noise. If the cosmos tapped a drum, we will hear it again. If we only heard the building settle, we will learn how to tell those sounds apart next time. Either way, the next clear nights will speak more honestly than 1,000 comment threads. Hold the wonder, keep the questions, and carry a notebook for when the sky answers in its own slow voice. Every good mystery has a map drawn in the margins. In this story, the margin map is a sweeping framework that tries to stitch sacred numbers, planetary motion, and ancient poetry into one geometry. It is called a hyperdimensional solar system by its champion, and whether you buy it or not, it has shaped how thousands of people are thinking about 3i Atlas. So let us walk through it carefully, fairly, and with both feet on the ground. The core claim begins with a single number, 591, not roughly, exactly 591. In this model, that number represents a kind of central rhythm in Earth days, attached to a hypothetical orbital domain that would sit between Mars and the asteroid belt. From that center, the model scales outward and inward using the golden number, dividing and multiplying, as if the solar system were a musical score written in proportional steps. Do that arithmetic enough times, and you land near several familiar orbital periods. That proximity feels spooky. It is also exactly where caution must enter. Here is the clean version. If you divide 591 by a simple factor, you find yourself brushing past Earth's sidereal year. Keep stepping down or up by the golden ratio, and you can nudge into the ballparks of Venus, Mars, and beyond. The model then layers on myth. Dante's celestial spheres and angelic orders are mapped to these proportional zones, as if medieval cosmology were a coded index to hidden dynamics. It is elegant, it is cinematic, and it is massively vulnerable to the many doors problem. When you let yourself try enough ratios, enough rounds of division and multiplication, you will open a lock by accident. What would need to be true for this to be a physical law instead of a pattern collage? First, the central number would have to point to something measurable in the world, not just in numerology, a resonance you can detect, a gravitational quirk that leaves fingerprints in asteroid families or spacecraft trajectories. Second, the near misses would have to tighten as measurements improve, not loosen. When you add better ephemerides, the fits should get sharper. Third, the framework should predict something new before we see it, in a way that a rival model would not. Prediction is the currency that pays for attention in science. Not post hoc narration, but receipts. Now put 3i Atlas back into the picture. Fans of the framework point to the object's rotation, 16.16 hours. Multiply that out, and you get 969.6 minutes, a number that people love to connect to an ancient lifespan recorded in a religious text. Add the golden number squared, and you find ratios close to that rotation period when compared to Earth's year. Near, not exact. Near enough to tickle a brain that already likes patterns. Far enough that a hard-nosed analyst keeps the pen capped. Before you roll your eyes or raise your banner, consider a softer value in all this. Even a wrong model can be useful if it tells us where to look and what to measure. A speculative framework that shouts, watch perihelion, watch the angles, watch the harmonics of timing, can act like a flashlight. It can also, and this is important, predict the behavior of the audience. It says, the public will pay attention to beautiful numbers and ancient names. The public will amplify coincidences that rhyme with myth. That prediction has already come true. Understanding it gives us leverage to communicate clearly, without being steamrolled by vibes. So, how do we treat a fringe atlas with respect and boundaries? We extract testable statements and throw away the rest. If the model says pulses tied to 5, 8, and 13 will repeat at specific phases, we can check that with clocks and telescopes. If it says a certain date will bring a sharp change in brightness because of an alignment with a sacred angle, we can plot the light curve and see. If it says a hidden orbital domain exists at a specific period, we can look for gravitational echoes in real datasets. What we do not do is let flexible story math replace hard uncertainties. We keep error bars where they belong, in the sentence, not the footnote. There is also a humility lesson hiding here for all of us who love clean mechanisms. History is full of outsiders who guessed the right answer for the wrong reasons. It is also full of confident mainstreamers who dismissed clues because they arrived in strange packaging. The fix is not to abandon skepticism. The fix is to treat weird packages like any other proposal. Open them, pull out the parts that can be weighed, and put the rest on a shelf without setting the house on fire. Let us be precise about one more thing. Pattern matching is not a sin. It is the beginning of almost every discovery. You notice a rhythm, then you try to break it. If it survives abuse, you build a model. The hyperdimensional map flips that process. It starts with a desired rhythm and collects supporting echoes. That is backwards. Tempting, theatrical, and backwards. If it wants to move from theatre to theory, It needs to risk being wrong in public with predictions that can fail cleanly. Where does that leave 3i Atlas? With chores, not chance. We will check the spin again when the object returns to view. We will track whether any putative pulses line up with the nucleus, like clockwork, or drift like weather. We will compare spectral scale lengths in a way that ties chemistry to geometry, rather than to poetry. And if a beautiful number seems to fit, we will say the number slowly, with its uncertainty attached, and ask, did this match sharpen as data improved, or did we round our way into romance? Here is the most generous reading I can offer. Even if the grand map turns out to be a story about us more than about the sky, it has already taught us something vital about attention. Numbers, myths, and coincidence are high-octane fuel. They can carry a science story into places dry plots never reach. Our job is to burn that fuel clean, keep the drama, keep the human resonance, but root the energy into questions that survive the morning after the mystery fades. If we do that, the Atlas of the Fringe becomes what a good atlas always is, a guide to roads worth walking and cliffs to avoid. When people hear that observatories went quiet, the imagination rushes to hidden hands. Sometimes the explanation is less theatrical and more annoying. Hardware wears out, teams rotate, budgets wobble. But the effect on trust is the same. You feel a gap just when you needed clarity. So let us walk through the gear that matters for 3i Atlas, what each instrument is good at, why interruptions happen, and how to think about motives without slipping into fantasy. Start with the Solar Dynamics Observatory. Its mission is the Sunday. It stares in extreme ultraviolet wavelengths that reveal loops and flares and coronal fireworks. It is an incredible machine for solar weather. It is not a comet hunter. Still, when an interstellar object skims the inner system, any sun watcher can become a witness by accident. That is why a maintenance window feels unlucky. You want every sensor online in case a stray frame catches something near the limb. Routine pauses are baked into spacecraft life, though. Gyros need calibrations, software gets patched, data pipelines get cleared. Engineers prefer to do that work when they will not miss scheduled targets. The universe did not check the maintenance calendar. Now the high-resolution imaging science experiment camera on the Mars Reconnaissance Orbiter. This camera sees Mars in stunning detail. At long range, it can still pick out large-scale features and bright points in the sky, but that requires a plan. Pointing a narrow camera at a faint-moving target is not like photographing a mountain. Your exposure must be tuned, your background must be understood, your timing must work around the orbiter's other jobs. The camera has had electronics problems and occasionally goes offline for safing. Repairs are conservative because no one wants to risk the whole orbiter for a stretch goal. On paper, you can imagine beautiful frames of an interstellar visitor from Mars orbit. In practice, you need a perfect stack of logistics and luck. Add European spacecraft to the mix. A Mars orbiter can grab context images of the sky. A mission cruising far from Earth can in theory see the target at a better angle during Earth's glare season. But instruments are designed with narrow goals. A spectrometer tuned for planetary atmospheres may not be optimal for faint comet. A star tracker might see the object but not record science-grade data. Teams must weigh risk and reward. Repointing costs fuel. Deep exposures cost time. Time costs other science. Even a yes decision may take days to filter through operations, and by then geometry has shifted. Ground-based telescopes are workhorses when the glare angle improves. They can run fast photometry to time pulses. They can split light into colors to measure gas species and dust behavior. They can coordinate with amateurs who supply cadence that big telescopes cannot, because small scopes can babysit a target all night without a crowded queue. During blackout weeks, though, everyone is playing defense. The sun is simply too bright. Even high-altitude observatories cannot beat that physics. Now, layer on the human factor. A government shutdown can furlough staff and delay data processing. A strike, a snowstorm, a power issue at a data center can slow the pipeline that turns raw numbers into public plots. None of those are diabolical. All of them are real. And when they stack near an exciting event, they create perfect conditions for doubt. The timing may be coincidence. To an anxious audience, coincidence is never just coincidence. Here is how to read a pause without losing your bearings. Ask 3 questions. First, what is the stated reason, and does it match the history of similar missions? If a camera had issues months before the story heated up, the current gap likely has a boring route. Second, what is the path back to normal? Are there estimates, and do they get updated as work proceeds? Silence breeds theories. Even a short weekly sentence can keep trust alive. Third, are there alternative assets that could fill the role? If other teams are trying and failing for geometry reasons, you know the limitation is physical. If no one else is trying at all, you should ask why. There is also incentive math that does not require villains. Institutions hate being wrong in public. When data are noisy, teams often wait for a second look rather than post a dramatic maybe. That caution is healthy for science and terrible for social media. Platforms reward speed and confidence. They do not reward careful caveats. So fringe voices often move first. They post with certainty. They go viral. By the time careful teams appear with nuance, minds have already chosen sides. That is not a conspiracy. It is a market mismatch between attention and accuracy. This does not mean we give institutions a free pass. If you sit on routine data with no technical reason, you lose the audience you eventually need. If you know you will go quiet during a crucial window, you can publish an observation plan that explains what will and will not be possible. You can give the public a checklist so they can follow along without inventing ghosts. That is not only good outreach, it is also a shield against the next rumor wave. A plan on record beats a vacuum every time. So, where does that leave us in the middle of the interruptions? With the same compass we use for everything in this documentary, translate capabilities into expectations. The Solar Dynamics Observatory is not a silver bullet for a faint visitor. The Mars camera could, under special conditions, show structure, but reliability issues reduce odds. European craft may have angles we lack, yet bandwidth and instrument design limit what can be shared quickly. Ground observers will carry much of the weight the moment the sun steps aside. One more thought before we move on. Uncertainty invites stories, but it also invites community. The best counterweight to gaps is a global network of eyes and minds who agree on a few simple rules. Share raw data when you can. Document your processing clearly. Post predictions before measurements so there is a fair test. Celebrate null results because they narrow the possible. When institutions stumble, that community becomes a bridge rather than a bonfire. In short, interruptions happen. Some are mechanical, some are bureaucratic, a few are just lousy luck. The smart response is neither to trust blindly nor to assume malice. It is to map what each instrument can and cannot do, keep pressure on teams to communicate, and build redundancy across independent observers. That way, when the sky opens again, answers do not depend on any single camera or any single gatekeeper. They depend on the sky and on us being ready to hear what it says. Stories do not just happen, they propagate. In the vacuum between an exciting claim and a hard confirmation, leaks bloom like algae in warm water. Some are sincere previews, from people who want the truth out faster. Some are performance art built to farm attention. Some are a mix of memory, hope, and a hand on the scale. To navigate that mess, we need a simple map for how information slips, how it sticks, and how to tell a seed from a weed before it overruns the field. Begin with the drought. A dramatic event lands during a period when official instruments are quiet or distracted. The first wave is speculation. Then an image, a graph, or a paragraph appears from someone adjacent to the action. It might be a hobbyist with access to public data. It might be a contractor with a screenshot from a working console. It might be a researcher with a draft analysis waiting for a co-author to wake up. The leak arrives with urgency and a tone that says, "Look now," before it vanishes. That tone is powerful because it frames you as an insider. Insiders feel special. Special sticks. But urgency is not provenance. A reliable leak has bones. It has timestamps that can be cross-checked against public ephemerides. It has coordinates any skywatcher can point to. It has enough context that another person can attempt the same extraction on their own copy of the data. A weak leak hides behind collage. It screenshots a screenshot. It crops the axes off a plot. It invokes unnamed sources and drowns you in adjectives. The difference is not subtle once you train your eye. One invites replication, the other demands belief. There is a recurring pattern in space rumors that is worth learning by heart. First, the tease, then a confident claim packaged for maximum shareability, then a short window of virality where debate is theatre and receipts are thin. Finally, either a quiet walk back or a substitution where the original claim mutates into a nearby cousin that is harder to falsify. If you have watched the cycle enough times, you can almost set your watch by the pivot. The trick for us is to interrupt that loop by asking for one thing early that opportunists hate to provide, raw or primary data, or a traceable route to it. Why do even smart people fall for the same formats? Because leaks often contain a kernel that later turns out to be real. Not because a hidden hand planned it, but because the universe is noisy and big stories have many observers. An amateur may indeed spot a faint smudge hours before a team posts calibrated frames. A grad student may plot a curious line ratio on a personal account while their supervisor waits for a more polished release. Those partial truths train our brains to treat all early whispers as potential gold. The antidote is not to ignore whispers, it is to weigh them by the one question that never goes out of style. Can someone else check this without the original leaker's special access? Let us make that test simple enough to keep in your pocket. If a leak claims timing, ask for the exact minute and the clock standard. If it claims brightness, ask for the aperture, the exposure, and the comparison star. If it claims position, ask for the reference frame and the uncertainty. If the answers are hand waves, move on. If the answers are crisp, someone somewhere will try within hours. The internet is not short of capable people with telescopes, code, and insomnia. There is also the social architecture of leaks. Fringe communities amplify what the mainstream ignores not just out of contrarian spirit, but because it rewards identity. You did not wait for permission. You saw first. That feeling is intoxicating, and it pushes creators to package their drops like cliffhangers, bold thumbnails, dramatic music, a tone that suggests institutions are slow at best and deceitful at worst. Sometimes institutions are slow, sometimes they are defensive, but experience teaches a harder lesson. Drama is an unreliable proxy for truth. Some of the most important science slides into the world looking like a boring PDF at 2 a.m. This is not a call to retreat into dry channels. It is a call to demand, formatting that respects your intelligence. A good leak for a story like 3i Atlas looks like a modest post with a plot, a caption that explains what changed since last week, and a link to data anyone can fetch. It includes a prediction for what should happen next if the interpretation is correct. It gives a concrete way to be wrong. That last part is crucial. When a leaker shows you the conditions under which their claim would fail, they are showing you they care about reality over reputation. Now, what about the argument that leaks exist because gatekeepers hoard? Sometimes they do. Sometimes data rights and publication culture slow the flow to a crawl. Sometimes teams fear being scooped and sit on results until a conference. Those are fixable behaviors. Publicly funded missions can and should post observation plans early and outline what will be released and when. They can publish reduced products with clear caveats rather than waiting for perfection. They can reward early sharing in tenure and promotion processes. When institutions do that, they blunt the demand that only dramatic leaks can satisfy. Even with reforms, the leak ecosystem will not disappear. It is baked into modern media, so we can make it work for us. Treat leaks as hypotheses generators, not as verdicts. Let them tell you where to look, what to time, and which bands to split when the blackout ends. Use their specifics as a shopping list for observations that either lock the story in or gently take it apart. In that sense, a culture that tolerates leaky teasers can still produce clean science, as long as the next step is measurement, not mythology. Here is the pledge we keep as this documentary rolls forward. We will surface leaks that pass the bones test and immediately translate them into checks the broader community can run. We will ignore high-gloss packages with soft spines. We will not punish honest corrections. If someone posts a confident claim on Monday and revises on Thursday, after better data, that is not losing. That is science in public. The reward should be trust, not dunking. In the end, the leak pattern is just a reflection of human impatience braided with our hunger for wonder. The sky moves on a schedule indifferent to our feeds. Our job is to build bridges from the viral moment to the verifiable moment without falling into the river in between. When the next whisper arrives, we will listen, then test, then decide. That rhythm keeps curiosity bright and keeps us from being passengers on someone else's roller coaster. When astronomers say an object is weird, they usually mean it nudges the edges of the model. 3i Atlas does not nudge, it elbows. One oddity can be chalked up to chance. A handful can be stitched together with patience. A pile begins to feel like a new category. Our job is to stack the anomalies in one place, translate each into plain language, and show the most sensible natural outs for every single one. Then we step back and ask whether the pile still looks ordinary from a distance. Start with the tail that points the wrong way. Comets usually wear tails that stream away from the sun, because sunlight and the solar wind push dust and gas outward. 3i Atlas has shown a faint component that leans toward the Sunday. Natural Path one says heavier chunks can be launched sunward by jets for a short distance, before light pressure and gravity turn them around. Think of a fountain throwing pebbles upwind on a gusty day. It is possible. It is not common. The tell would be slow-moving grains that curve back after a short run. That is testable with time series images once the glare eases. Now, the metal lines. Spectra from earlier in the season carried strong nickel features without the usual iron companions. In stellar factories, nickel and iron are born together, so their ratio tends to be predictable. Natural path. One says chemistry near the nucleus could favour formation of nickel-bearing molecules that break apart in sunlight more easily than iron compounds. Carbon monoxide environments can do strange things to metals. Natural path 2 says iron is present but below detection in the measured bandpasses. Both explanations need follow-up with deeper, cleaner spectra. If nickel stays bold while iron stays missing across instruments and epochs, the eyebrow stays raised. Composition is the third surprise. Many comets are water-forward with carbon dioxide and carbon monoxide as side players. 3I Atlas appears to run heavy on carbon dioxide with water, a minority player in the early release. Natural path 1 says it formed in an extremely cold nursery where carbon dioxide ice was abundant. Natural path 2 says we are seeing seasonal behaviour, with different ices turning on as the sun warms new regions. If the water fraction rises sharply as the object swings inward and rotates new terrain into sunlight, that will support the seasonal idea. Water production has its own drama. Early looks suggested a sudden jump to tens of kilograms per second, while the object was still far from the sunday, that is a fire hydrant at a distance where most comets dribble. Natural path 1 says buried pockets of volatiles hit a thermal threshold and popped. Natural path 2 says our earlier stack of images missed a gentle coma that only became obvious after a delay. Both can be tested with careful light curves and repeated gas measurements after re-emergence. If the hydrant returns with a rhythm tied to rotation, that argues for vents. If it arrives in unpredictable bursts, subsurface pockets gain ground. Size and mass make the next knot. Brightness-based estimates bounced from sub-kilometre scales up to several kilometres, because brightness depends on both size and reflectivity. Meanwhile, dynamical arguments suggested a hefty mass to resist jet thrust without wobbling off the predicted path. Put those together, and you get a range that is hard to reconcile. Natural path 1 says that the surface is darker than we assumed, so it is bigger than it looks. Natural path 2 says the nucleus is a compact chunk with higher density than a fluffy snowball. The fix is straightforward in principle. We need sharper constraints on shape and albedo from high-resolution imaging and better fits to any non-gravitational accelerations in the orbit. Spin lives in the middle of the puzzle like a mischievous cat. The rotation near 16.16 hours led to numerology flourishes we already fenced with. Leave the poetry aside, and the physics question becomes simple. Do activity features repeat on that clock? If jets rotate into view like a lighthouse, all the other oddities should get a little more boring. Nickel plumes would wax and wane with the turn. The tail component that points sunward would sync to the same rhythm. That is exactly the kind of pattern amateurs can help nail down. Once the object clears, the Sunday trajectory adds flavour without deciding the case by itself. The orbit is retrograde and skims close to the plane where planets live. A random interstellar object can do that, but the odds are low compared to steeper, weirder inclinations. Natural path 1 says low odds are still odds, and we got the rare draw. Natural path 2 says dynamical interactions long before discovery nudged the approach toward that plane. A technological path would whisper that the alignment is tactically handy for touring planets. We do not have to pick that whisper. We only need to remember that outbound behavior will either look cleanly ballistic or not. Early inactivity versus later frenzy is another friction point. Stacked frames before discovery looked asteroid quiet, then activity spiked. Natural path 1 says the coma was too faint to pick out early and only later crossed the visibility threshold. Natural path 2 says fresh surfaces cracked open and flipped the switch. This is a lesson in thresholds. Many apparent discontinuities in space turn out to be our detection limits, not the world flipping from off to on. Better cadence after re-emergence can teach us where the true ramp lives. Here is a helpful way to hold the pile without getting dizzy. Treat each anomaly like a coin weighted slightly toward surprise. Flip 1 and heads is rare but not shocking. Flip 5 and getting all heads feels awkward. Flip 10 and you start checking the coin. The only way to tell if the coin is fair is to measure more flips with better tools. That is what December offers. Watch the tail geometry. Recheck nickel and iron. Track water and carbon dioxide with time. Pin the spin. Lock the orbit. None of that requires belief. It requires patience and a lot of coffee. If the numbers fold back toward normal as methods improve, the pile will collapse into a tidy stack of lessons about interstellar comets. If the numbers stay spiky and lined up in ways natural models strain to match, the the conversation moves a notch toward the deliberate. Either way, the anomalies have done their job. They forced us to write down predictions, to coordinate observers, and to care about the difference between a beautiful story and a stubborn dataset. That is how weirdness pays rent in science. It makes us better at seeing what is actually there. If you wanted to change your path through a star system with the least effort and the most stealth, where would you step on the gas or the brake? Right where gravity is strongest and your speed is highest. That trick has a name that sounds like a wizard but is really just clean mechanics. The Oberth effect. It says that a push or a pull delivered at top speed buys you more change in energy than the same push given in the slow outskirts. Spacecraft use it all the time. A burn near a planet's closest approach stretches or shrinks or twists the next leg of the journey far more efficiently than a burn in deep space. Now flip it. A reverse Oberth is just using that same sweet spot to slow down rather than to speed up. If an interstellar visitor arrives on a hyperfast track and performs even a modest deceleration at closest approach to the Sun, it can lose enough energy to become a long-term resident instead of a flyby. That single nudge also rotates the outgoing path in ways that are obvious on paper, but hard to see while it is happening, which is why the far side of the Sun is a perfect curtain. If you were going to change your status from passerby to neighbour without drawing attention, you would do it when Earth's line of sight is blinded by glare and the background is a wall of photons. So what would we expect to see after such a move? 3 simple tells. First, outbound speed. Before perihelion, we can fit the inbound path and estimate the energy the object carries. After perihelion, if nothing deliberate happened, the outbound speed at the same distance should match within the wiggle room allowed by natural forces like jets of gas. If we find the outbound flow noticeably slower than the inbound, by more than realistic outgassing could provide, something pumped the brakes. Second, turning. A small push applied at the right moment can swing the outgoing direction a little. We watch the sky position over weeks and fit a new track. If the track cannot be reconciled with standard non-gravitational tweaks, the plot thickens. Third, timing. A burn centered near closest approach is not a fuzzy, months-long drift. It is a sharp event. We should see the biggest discrepancy cluster right after the object emerges. Natural objects do cheat a little on gravity-only paths. Sunlight heating one side more than the other can force out gas and dust in an uneven way. That acts like a tiny thruster. Comet modelers fold that into the orbit as extra terms that nudge the fit. But those nudges have signatures. They ramp up and down with distance from the sunday. They often align with the spin in a predictable way. They rarely deliver a crisp, step-like change in energy right at perihelion that persists for months without a clear physical source. That difference matters. Outgassing is messy, gradual, and tied to surface activity. A deliberate maneuver is brief, concentrated, and tuned to the physics jackpot. Here is a plain language picture. Imagine riding a skateboard down into a bowl. At the bottom, you are moving fastest. If you kick hard there, you rocket out higher than if you had kicked the same amount near the rim. The sun is the bowl. Perihelion is the bottom. The kick can be forward to go faster or backward to slow down. Either way, the energy change is amplified. If 3i Atlas kicked backward in the bowl, our post-perihelion measurements will feel it as lower than expected outbound speed and a path that does not quite match the tidy mirror image we would get from pure gravity. Could a natural jet pretend to be a reverse Oberth? It would have to erupt at exactly the right time and direction, with sustained thrust aligned to the motion, and with a magnitude at the high end of what volatile vents can plausibly deliver for an object of this brightness and size. That is a narrow target. Not impossible. Narrow. The good news is, we can test the plausibility because gas production rates, jet geometries, and spin states leave fingerprints in the light and in the spectra. If the numbers say the vents were anemic, but the path changed like a champion thruster fired, you know the story is off. What measurements do we need to pull this off in the real sky? First, high-cadence astrometry, which simply means careful position measurements night after night to chart the exact track against background stars. Tiny deviations accumulate into a readable pattern. Second, a clean brightness curve to see whether any sudden changes in activity occurred as it emerged. A sudden fade or flare could signal jet behavior that helps or hurts the outgassing explanation. Third, spectra across key gas lines to estimate how much stuff is being thrown off and at what characteristic scales. Those numbers feed straight into the question, can natural vents deliver the required shove? There is also a subtle angle we cannot ignore. If a burn happened, it may not have been a single clean pulse. A smart craft could spread the maneuver over hours to smear the signature. Even so, the energy accounting must close. You cannot hide the total change. You can only blur the moment-to-moment curve. Our response is the same. Integrate over days to recover the net difference and refuse to be distracted by small weather in the light curve. Why does this matter beyond the thrill? Because reverse Oberth is a fork in the road for interpretation. If the outbound energy matches the inbound within conservative bounds, the artificial hypothesis falls a notch and we look harder at natural chemistry and geology to explain the earlier oddities. If the outbound energy is lower than expected in a way that outgassing cannot pay for, the needle moves. Not to certainty, but to a higher level of interest that justifies mission studies, deeper coordination, and all the sober steps that follow a surprise you can calculate. One more question that keeps people up at night. Could a reverse Oberth aimed not at capture but at retargeting put Earth into play quickly? In principle, yes. The same efficiency that lets you grab a stable orbit also lets you pivot onto a new course with less fuel than you might guess. The calendar math for close approach would depend on the exact vector and the amount of braking. That is why precise early post-perihelion tracking is not optional. It shrinks the family of future paths and tells us whether any of them thread near our neighborhood in the coming months. In a way, this is the cleanest chapter in the whole story. We do not need to argue about symbols or anniversaries here. We only need to measure how fast something came in, how fast it goes out, and how straight the mirror is between those two halves. The Oberth effect is not mystical. It is a lever built into gravity that any engine can use. If 3i Atlas pulled that lever on the far side of the sun, the math will tell on it. If it did not, the math will shrug. Either way, we come out of the blackout with a yardstick in our hands and a yes or no question the sky is ready to answer. Could a cautious intelligence visit a new star system and leave almost no fingerprints? That is the dark forest thought experiment in one sentence. Picture the universe as a nighttime wood, where every rustle might be a hunter. The safe strategy is silence. If you must explore, you move like a leaf, you look like a rock, and you act when the watchers have their backs turned. It is not a claim about 3i Atlas. It is a lens we can hold up briefly to see whether the current facts would make tactical sense to something that does not want to be obvious. Start with the disguise. In a dangerous cosmos, you do not arrive flashing beacons. You choose trajectories that look ballistic. You keep a composition that reads like natural ice and dust. You let sunlight do most of the talking, so your motion can be explained by outgassing and radiation pressure. If you must communicate, you pick a channel that bypasses gatekeepers and rides on public curiosity. A handful of clean numbers at a culturally loaded moment might do that job. Not proof, a plausible playbook. Next, the route. If you wanted to tour a system efficiently, you would skate along the plane where most planets live. A low inclination path gives you repeated chances to sample atmospheres, magnetospheres, and moons. It also keeps your options open for small course changes that create large differences in who you can visit next. A retrograde orbit, the opposite direction of most local traffic, feels counterintuitive. Tactically, it has perks. You meet planets head-on, which can be useful for high relative speed flybys and for minimizing time within their detection envelopes. Again, not proof, just a line of reasoning that makes the observed geometry feel less random. Then the curtain. If you were going to change energy, slow to stay or pivot to somewhere sensitive, you would choose the place where no one can watch. The far side of the sun, from the only civilization we know about, fits that requirement too perfectly to ignore as a scenario. Gravity gives you a bonus at perihelion. Glare gives you cover. You act, then you let the math carry you out of the blind spot. Anyone who wonders what happened must infer it from before and after snapshots. That is how you would design stealth if you had millennia to practice it. Communications are the strangest part of the frame. The safest probe never broadcasts at all. But there is a second strategy, call it breadcrumb theatre. You leave ambiguous traces that can be publicly debated for months without a definitive refutation. You seed numerically pretty patterns that a large audience cannot resist. You let institutions stumble over outages and delays so that people learn to distrust centralized explanations. Why do that? Because if you ever wanted to reveal yourself later, you would prefer a world already warmed up to the possibility, already arguing the right questions, already building the tools to see. You are doing disclosure without ever taking responsibility. There are important counters. Nature can fake stealth without trying. Comets, by definition, look like comets. Outgassing produces non-gravitational nudges that mimic small thrusters. Solar glare blinds observers on schedules that have nothing to do with intent. Humans layer meaning on coincidences faster than any alien strategist could. If you sift enough events, some will align with our rituals and numbers by accident. The dark forest frame is attractive precisely because it rides on our fear and our love of narrative. That is a warning, not a verdict. So how do we keep the thought experiment in the toolkit without letting it hijack the toolkit? We treat it as a set of testable ifs. If a reverse energy change appears near perihelion, with no plausible outgassing budget, stealth gets a point. If the post-blackout trajectory lines up with a path that offers efficient planetary intercepts, stealth gets another point. If, on the contrary, the path is a clean mirror of gravity and the spectra behave like ordinary chemistry, with the dials turned a little weird, stealth loses ground. The frame is not a worldview. It is a scoreboard with boring criteria. Ethics matter in this discussion too. Even if something more than a comet is in play, the dark forest story does not license panic. A cautious civilization that has mastered stealth likely mastered patience. The best response from us is not to flail or threaten. It is to observe with care, share data openly, and avoid doing anything that looks like a challenge. Non-provocation is not surrender. It is prudence while we gather enough facts to decide whether this is a tourist, a surveyor, a relic, or a ghost. There is also a humble possibility. The dark forest could explain not a clever visitor, but our own behavior. We act like residents of a risky galaxy when we censor uncomfortable ideas, when we bury anomalies under ridicule, when we let institutions choose silence over messy transparency. That is self-imposed stealth. The fix is simple and hard at once. Publish plans, share uncertainties, invite replication. In a forest, the safest campfire is the one many eyes can see. Here is where this lens earns its keep. It reminds us to look for strategy in the data, without inventing strategy when the numbers do not need it. It trains us to separate cinematic coincidence from mechanical consequence. It keeps a spot on the table for the possibility that something smarter than we are is playing the long game, while insisting that the next move is still ours. Measure outbound energy. Track the path. Split the light. If the evidence tips toward ordinary, we close the book on this chapter gracefully. If it tilts toward deliberate, we open a new book with cool heads and a wider circle at the table. In short, the dark forest is a thought experiment, not a trap. Use it to pose sharp questions. Retire it when the answers arrive. When the glare fades and the plots start to fill in, the forest will either thin into a normal grove of comet physics, or it will deepen into something else entirely. Either way, we walk forward with curiosity first, imagination close behind, and fear on a short leash. Why did the October 13th claim detonate across the internet faster than any light curve or spectrum this season? Because dates are sticky. They snag memory and braid events together whether or not the physics cooperates. On October 13th, 1917, tens of thousands in Portugal reported the sun, dancing, changing colour, plunging, and returning. Some clothes dried in minutes after rainfall. Others saw nothing unusual and blamed suggestion and optics. 108 years later to the day, a rumoured Fibonacci signal appears while our best eyes blink or look away. Could this all be coincidence? Or are we being played by our favourite instrument, our pattern-hungry cortex? Start with the power of an anniversary. Commemorations act like amplifiers. Tie your message to a date that already hums, and you inherit a choir. Even if nothing causal links the two, the shared timestamp welds them in memory. Psychologists call this binding. It is how you remember where you were when you heard a headline. It is also how rumours get legs. The stronger the cultural hook, the less technical rigour you need to spark headlines. Numbers and sacred days are high-octane fuel. Now take a breath and separate three different questions. What happened at Fatima in 1917? Why did the new claim choose that date? What does that choice tell us about the sky? The first is a historical fight we are not going to settle here. Atmospheric optics can do strange things near the sun. When people stare through thin cloud and dust, group expectation can colour what individuals report. Yet physical claims like drying clothes and temperature swings remain uncomfortable for clean debunking. The record is messy, not worthless. The second question, why choose the date, has an easy answer in human strategy. If you want to be noticed, aim for the anniversary. The third question, what does it tell us about space? Very likely nothing at all unless you already believe the cosmos schedules around our calendar. So why spend a chapter on this? Because understanding how synchronicity works in us is the best defense against being steered by it. The brain is a pattern completion machine, running on 20 watts and millions of years of practice. When two events share a time, a number, or a symbol, We draw a line. Sometimes the line is real. Tides and the moon share both time and cause. Sometimes the line is narrative only. We still act like the connection is solid because it feels solid. Feeling is not evidence. Feeling is a flag that says measure more precisely. Consider the 108 drum beat that shows up in religious traditions and in enthusiasts' number games. Multiply and divide it, and you can land on many attractive figures, 400, 232, 216, and then go looking for them in architecture and orbits. The many doors problem lives here rent-free. If you try enough keys, one will open a lock by accident. The fix is pre-registration of your test before you count. You say out loud what will count as a hit and what will count as a miss. You do not move the goal when the first attempt lands near, but not on target. Could an intelligence that studied us choose to speak in our calendar tongue? Absolutely. If your aim is to bypass journals and talk to crowds, you speak in birthdays and holidays, not in line widths and absolute magnitudes. That is a clever tactic. It is also indistinguishable from a human hoaxer with the same goal. Strategy does not prove agency. It only raises the bar for the next measurement. We answer strategy with mechanics. Did the object's energy change? Did the spectra shift in ways consistent with a timed jet or an engine? Did independent instruments record the same beat at the same minute? If not, the anniversary is a garnish, not a meal. There is a deeper reason this matters. Synchronicity can make skeptics reckless too. Faced with a pile of coincidences, some people swing hard the other way and punish anyone who hesitates to call it all nonsense. That is not scientific caution. That is allergic reaction. The right posture is boring and brave at once. Hold the possibility that meaning sits in the stack while you demand measurements that can survive error bars and replication. That is harder work than shrugging or swooning. It is also the only path that leaves you wiser next time. Let us talk practical guardrails you can use any time a cosmic story ties itself to a date. First, ask whether the physical system has any reason to know our calendar. The answer is almost always no. The sun does not care about our weeks and months. Orbital geometry cares about angles and energy, not anniversaries. Second, ask whether the same claim would land without the date sugar. If you strip the Fatima parallel from the Fibonacci rumor, are you still intrigued by the evidence? If not, you learn something about marketing more than astronomy. Third, watch for sliding criteria. If a promised event misses the hour, the day, or the week, does the claim stretch to keep the spotlight? Elasticity is a tell. The most generous reading of all this is not mystical, it is pedagogical. The Fatima Echo brought millions of people into a conversation about attention, instrumentation, and inference. It gave non-specialists a reason to learn words like perihelion and light curve. If we do our job well, those people leave with better instincts about how to weigh claims. The anniversary got them through the door. The methods should convince them to stay for the right reasons. So here is the deal we make with dates. We can use them to open hearts, as long as we do not let them close minds. We can acknowledge the poetry, as long as we keep the prose crisp. When the object reappears from behind the sun, the calendar will fall quiet. The plots will get loud, and the answer to the only question that matters, did something measurable happen that ordinary models cannot pay for, will not care what day it is. Hold curiosity, hold skepticism. Hold space for wonder that does not depend on numerology to feel thrilling. The universe is allowed to be both beautiful and indifferent to our rituals. If an intelligence chose that date on purpose, the outbound energy and the repeated beats will tell us soon enough. If not, we will file the anniversary under memorable coincidence and move our attention back to the stubborn arithmetic of light and motion. Either way, we step forward more clear-eyed than we were yesterday. Before we argue about what might have happened in the glare, we set the table with what we actually have from the inbound leg. This is the part many skip because it feels quiet and technical. It is also the bedrock. Positions measured against background stars, brightness measured night after night, spectra that separate light into chemical fingerprints. These are not vibes. They are the pieces that let us say later whether anything changed in the dark. Start with the simplest pillar. Astrometry is the practice of pinning an object on the sky with enough precision that a computer can fit its path. Teams around the world fed positions into public databases through late summer and early autumn. The fits converged on an interstellar track with high incoming speed and a retrograde sweep close to the planetary plane. Uncertainties tightened as more nights came in. That matters because a tight inbound solution becomes the mirror we hold up to the outbound. If the mirror image does not match, we know where and by how much it bends. Photometry is the second pillar. Telescopes measured how bright 3I Atlas appeared across wavelengths and phase angles. Early stacks suggested almost no extended coma, which made the object look asteroid-quiet for a short window. Weeks later, the brightness climbed, and the coma became obvious. That shift can be interpreted as a threshold effect. The dust and gas may have been present, but too faint for the earlier stacks. Or vents may have opened as sunlight reached fresh terrain. Either way, the inbound light curve is now a reference trace. Outbound behavior that departs sharply from it will need a cause. Spectroscopy gives the story color and texture. Observers split the light and found strong features from carbon dioxide and carbon monoxide, with water apparently playing a smaller role than in many homegrown comets. Lines from cyanide and nickel added intrigue, especially the nickel without clear iron. Calibration matters here because different instruments and reductions can make weak features look stronger or softer. Even so, multiple teams saw a carbon-heavy personality. That is a clue to formation history. It also sets the stage for a check after perihelion. If the same bands bloom or fade in unusual ways later, that will be a physical change, not a processing ghost. Rotation came into focus through repeating patterns in the brightness. A period near 16 hours emerged from careful timing of subtle modulations. You can think of this as a clock painted by sunlight across a lumpy surface. When a vent or a patch of fresh ice rotates into view, the light ticks up. When it rotates away, the light dips. The period is not a guess. It is a measured drumbeat with uncertainties you can write down. That gives us a tool. Any claimed pulses or odd flickers later that ignore the rotation drum should be treated with skepticism. Any changes that lock to the period deserve extra attention. Dust behavior rounds out the inbound package. Images showed broad dust structures that respond to solar radiation pressure and to the object's motion. Some frames hinted at a sunward-leaning feature that could be heavy grains launched against the flow for a short run. To test that idea, we will need time series that follow the same grains across hours. On the inbound leg, those sequences were limited by geometry. Even so, the presence of mixed grain populations is clear. Small particles blow away easily and draw graceful tails. Larger pieces plod along and paint denser fans. This is normal comet physics with a few knobs set to interesting. What about mass and size? Those are always hard from afar, because brightness conflates reflectivity and area. Early estimates spanned from sub-kilometer to a few kilometers for the nucleus, with mass arguments suggesting a robust object if jets were as strong as the gas numbers implied. None of that is decisive. It does provide bounds for later energy accounting. A small dense object and a large fluffy object respond differently to the same thrust. If outbound tracking demands a push that the measured gas could not provide without exploding the mass budget, the natural explanation will feel strained. We should also mark the cleanest negatives. Inbound radar opportunities were poor. That means no direct size echo to anchor the photometry. High-resolution imagery of the nucleus did not materialize before the blackout. That means no shape model to explain the light curve with geometric confidence. These gaps are not shameful. They teach humility about what we can and cannot claim. They also point to the most valuable wins when the object returns. Even a coarse shape constraint would unlock better models for jets and torques. Taken together, the inbound packet paints a consistent portrait. Interstellar origin with a fast approach. Retrograde motion close to the ecliptic. Activity that woke up across 2 weeks. Carbon-heavy volatiles with water rising more slowly. Nickel lines that ask for another look at iron. A rotation period we can test against. Dust that behaves like a mix of light and heavy grains. None of this proves anything exotic. All of it is precise enough to become a ruler. Here is how we will use that ruler. We will project the inbound orbit forward as if nothing unusual happens, and compare each nightly outbound position. We will forecast the brightness based on distance and phase, and check whether the real curve sits above or below the line in a way that natural activity can explain. We will compare spectral band strengths against the inbound baselines, and ask whether chemistry is evolving smoothly or lurching. We will fold all photometry on the known rotation and look for features that stay fixed in that clock. The work is not glamorous, yet it is the heart of the reveal. Dramatic claims stand or fall on these quiet comparisons. There is a social benefit to this discipline as well. When you show your homework in public, down to the calibration stars and the code that measured the period, you build a shared reality that rumors cannot easily erode. Amateurs and professionals can reproduce each other's plots. Disagreements collapse to genuine differences in data or method, rather than to tone and trust. For a story as charged as this one, shared reality is the oxygen that keeps the collective from suffocating under speculation. So, The verdict on the inbound leg is clear. We have enough hard numbers to make December meaningful. The mirror is polished, the beat is timed, the chemistry is logged, the dust is sketched. Whatever emerges from the glare will either fit inside this frame with tweaks that feel familiar, or it will press against the frame in ways that demand a new chapter. Either result is progress. Either result makes the next night at the telescope worth the cold. When the object walks back out of the sun's glare, the temptation will be to sprint. Resist it. We need a plan that is fast without being frantic, precise without being paralyzed. Think of this as a coordinated heist against ignorance. Everyone has a role. Everyone has a clock. And the prize is simple. A clean, public answer to whether anything happened in the dark that ordinary comet physics cannot pay for. First, timing. The earliest recoveries will come from Southern Hemisphere observers with the best pre-dawn geometry. Small telescopes with sensitive cameras will grab position and brightness before big facilities spin up. That means we need Night 1 astrometry standards in plain English. Center on bright catalogue stars with well-known positions. Use consistent exposure lengths short enough to avoid trailing, long enough to beat read noise. Report times in coordinated universal time, down to the second. Post plate-solved images with solution residuals so others can verify. Early positions carry the most leverage in shrinking the family of possible outbound paths. Treat them like diamonds. Second, the light curve. We are hunting for two kinds of deviations: a gentle slide away from the inbound brightness model that natural activity could explain, and a sharper discontinuity that hints at a maneuver or an outburst. To catch either, cadence beats grandeur. 100 2-minute measurements spread across the night will tell us more than one glamorous deep exposure. Calibrate against nearby comparison stars of similar color to the object, and keep the same set across nights when possible. Fold every night's photometry on the known rotation period. If features line up with that drum, we are likely seeing vents. If a new feature ignores the clock, circle it. Third, spectra. The big questions are carbon dioxide versus water balance, the persistence or disappearance of nickel lines, and the scale lengths of cyanide. We want low resolution, high signal-to-noise scans across the bands where those species live, repeated night after night, if weather allows. Even modest spectrographs on amateur rigs can contribute if they post raw, bias, dark, and flat frames with their reductions. The signatures to watch are simple. If water surges as new terrain heats, that is seasonal. If nickel stays strong while iron stays shy across instruments, that anomaly hardens. If cyanide and nickel expand or contract in lockstep with the rotation, jets are painting the pattern. Fourth, tail morphology. Short exposures at high frame rate can freeze motion enough to trace individual dust features hour by hour. Stack with care using shift and add aligned on the nucleus. Draw streamlines over multiple nights. The sunward-leaning component, if real, should curve back under radiation pressure in a predictable arc determined by grain size and speed. If it does not, we misread the feature. If it does, we measure grain sizes and test whether earlier claims about unusual ejection velocities stand up. The win here is not a pretty picture. It is a map of dust flight paths with numbers on them. Fifth, orbit fits. As soon as the first 3 nights of positions exist, independent teams should publish preliminary outbound solutions with and without standard non-gravitational terms. Post the code and the assumptions. Show how much gas thrust would be required to produce any residuals. Compare those requirements with the gas production inferred from spectra. If the orbit wants more shove than the vents can plausibly supply, mark that on the plot in red. If vents can pay the bill, mark it in green. Keep this accounting updated daily for the first 2 weeks. Transparency here is oxygen. Sixth, cross-checks. Any strong claim must have a sibling test that could falsify it. If someone reports a pulse sequence, another team should attempt the same cadence on a nearby field star, processed identically. If someone claims a sharp step in brightness at a given minute, another team should align their timestamps and check for correlated weather, or tracking shifts. If a spectrograph finds a line, a second instrument should confirm the wavelength and relative strength before anyone puts adjectives on it. These are not insults. They are how we protect ourselves from friendly fire. Seventh, a public dashboard. Centralize the essentials: nightly best fit orbit plots, a rolling brightness residual plot against the inbound model, a rotation folded light curve panel, and a spectra panel with the keyband's integrated strengths. Keep it boring and brutally clear. Green track means within natural expectations. Yellow means interesting tension. Red means significant discrepancy requiring explanation. Update at a predictable time each day with a one-paragraph changelog. When rumors spike, point people to the dashboard rather than wading into every thread. Make truth easy to find. 8th, contingency for surprises. If a deviation crosses the red line, outbound energy too low by margins, vents cannot cover, or a track bend inconsistent with known torques activate a higher cadence campaign. That means calling in bigger telescopes for rapid turnaround spectroscopy, requesting radar pings if geometry allows, and coordinating global follow-the-sun photometry so the object is never unobserved for more than an hour. Publish the trigger criteria in advance so no one accuses anyone of moving the goalposts after the fact. 9th, communication discipline. Speak in numbers first, interpretation second. Always attach uncertainties. If you are guessing, say you are guessing. If you correct yourself, do it publicly and pin the correction where people will see it. Ban the word proof from your vocabulary for the first month. Replace it with weight, trend, and consistency. Our credibility is not a side quest, it is the mission. Finally, a reminder about pace. The story will feel loud in the first 72 hours after re-emergence. Then it will feel slow. That is normal. Real patterns need time to detach from noise. The win. The condition for this playbook is not a dramatic twist on day one. It is a week 2 plot where the coloured lines have stabilised and the community can agree on what the sky is doing without sharing a worldview. This is what shared curiosity looks like when it grows up. Not chaos, not chorus. A choir of instruments, each singing their part on pitch. If 3i Atlas did something we cannot explain with vents and sunlight, this plan will catch it clean. If it did not, we will still have one of the best observed interstellar visitors in history, and a public record of how to separate enchantment from evidence without losing either. That is the play. That is the point. Ready the telescopes. If you have never looked at a comet through a spectrograph, imagine turning starlight into a barcode. Each dark or bright stripe is a molecule or an atom saying, I am here. 3i Atlas arrived with a barcode that reads different from most icy wanderers we have met. The carbon bands were loud, water lines were quieter than expected for the distances involved. Cyanide was distinct. And then there was nickel without its usual partner, iron. That combination is either an invitation to learn about alien chemistry or a trick of geometry and sensitivity that better data will tame. Either way, this is where we talk about what those stripes mean in plain speech. Start with the carbon story. Many comets from our own backyard are water-heavy with carbon dioxide and carbon monoxide playing, supporting roles that get louder as the sun warms them. 3i Atlas looked carbon forward early. High carbon dioxide means the ice mix either formed colder than we are used to, or that the surface layers we saw first were rich in carbon compounds that turn on before water does. Colder formation would place its berth far out in its native system, a realm where carbon dioxide can freeze abundantly. A layered surface would suggest seasons on a spinning world of ice where different latitudes take turns as the spotlight, and different ices do the talking. Why does that matter? Because composition is a memory. The ice recipe records the temperature, pressure, and available gases where the object assembled. That is a postcard from another sun's nursery. If water stays a minority even as sunlight deepens, the cold cradle story hardens. If water surges and carbon dioxide steadies, the seasonal layering story gains ground. Simple to say, harder to measure because water is best seen in infrared bands that ground telescopes struggle with, while carbon dioxide hides in places even some space instruments cannot reach easily. Still, repeated nightly scans in accessible bands give us trend lines we can trust. Cyanide makes headlines because the word scares people. In comet chemistry, it is a workhorse tracer. When ices break apart under sunlight, cyanide shows up reliably and helps map how gas expands away from the nucleus. The distance over which the cyanide glow fades, the scale length, tells us how quickly molecules are being destroyed and how fast they are moving. Match that to the rotation period, and you can tell whether jets are feeding the coma in bursts or whether the whole surface is whispering evenly. Early cyanide in 3i Atlas had a distinct scale length that we will want to compare after perihelion. A change there will mean something changed in how the object is breathing. Now the nickel puzzle. Spectrometers reported clear nickel emission lines, while iron lines were faint to absent in the same epochs. In stars and rocks, nickel and iron are siblings. They condense together and travel together. Seeing nickel without iron is like hearing harmony without melody. Natural roots exist. Under particular conditions, nickel can form volatile compounds that break apart in sunlight more readily than iron compounds do, making nickel's light louder at certain distances. Carbon monoxide-rich environments help. Another route is more prosaic. Iron may simply sit below the instrument's detection threshold when spread thinly, while nickel happens to be right at the sweet spot for visibility in the measured bands. Here is how to keep this honest. We watch the nickel lines, and we keep scanning for iron with different instruments and integration times. If multiple setups keep shouting nickel and whispering iron across weeks and across geometries, the anomaly gets teeth. If iron appears as we change sensitivity and wavelength coverage, the early absence dissolves into a calibration artifact. That is not a letdown. It is a win because it teaches us where our blind spots were. There is a temptation to jump ahead and call nickel without iron an industrial signature, because one of the ways humans separate nickel on Earth involves carbonyl chemistry that produces volatile nickel compounds. That is a clever analogy. It cannot carry weight without a lot more context. Space is not a refinery, but it does host the same elements and many of the same molecules under fierce irradiation. Photochemistry can do odd things we might otherwise ascribe to factories. The right posture is to catalogue the lines, quantify their ratios, and compare them to models of gas flow and sunlight destruction, all the while inviting contrarian explanations to take their best shot. The dust and gas talk to each other in these data as well. When volatile ices sublimate, they drag dust off the surface. The ratio of big grains to small grains sets the shape of the tail and the amount of sunlight the coma reflects. If carbon dioxide dominates, you expect different jet strengths and grain sizes than in a water-dominated phase. That in turn changes how bright the object looks for a given gas production rate. The danger for storytellers is to compare brightness curves and gas curves without accounting for this coupling, then call the mismatch a mystery. The fix is to model dust and gas together and test the model against both the spectrum and the images. Rotation threads through all of this like a needle. A 16-hour period means vents, if they exist, will paint repeating arcs in both light and chemistry. Nickel and cyanide should wax and wane on that schedule, if a jet feeds them. So should the sunward-leaning dust feature if it is real. That is a clean prediction amateurs and professionals can test with synchronized observations. If the chemistry ignores the spin, either the source is wide and even, or our timing is muddy. Either way, the test pushes us toward clarity. Parity matters too. The spectrum before perihelion is only half the story. After re-emergence, the same bands read under different solar heating, different geometry, and possibly different active regions. We should not expect a perfect mirror image. We should expect continuity, unless something dramatic occurred in the blind spot. That is precisely why chemical baselines from the inbound leg are so valuable. They set our tolerance for weirdness. A slow drift is natural. A step change asks questions. Let us end with a small decoder ring you can carry into the next set of plots. Loud carbon dioxide with rising water over time suggests a cold origin with layers waking up. Persistent nickel with elusive iron across instruments stays interesting, but needs caution until more sensitive iron searches weigh in. Cyanide scale lengths that breathe with the rotation support jet-driven structure. A tail component that curves back the way radiation pressure predicts tells us about big grain ejection speeds rather than about exotic forces. None of these single threads decide the fabric. Together they weave a story you can feel with your hands. Chemistry is not as flashy as a leaked pulse count, but it is often more honest. Atoms and molecules do not care about our narratives. They absorb and emit light according to rules that have not changed since the first stars lit. If 3i Atlas carries a secret, the spectrum will either keep that secret carefully or let it slip, in ratios and rhythms we can measure. Either way, we listen. Either way, we learn. When the mind meets a mystery, it reaches for cousins. Comparison is a survival trick. It is also good science. So let us line up 3 famous visitors and bruisers next to 3i Atlas and extract the rule that kept astronomers sane through each uproar. Natural until non-natural is not a slogan. It is a way to stay curious without flipping the panic switch. Start with one Oumuamua, the first interstellar object we ever confirmed. It arrived small, faint, and fast. No coma was obvious. Photometry suggested an extreme shape or a complex tumbling state. Then the orbit fits needed a nudge, non-gravitational acceleration that looked like a gentle push away from the Sunday. No clear gas lines showed up. Theories bloomed. A fluffy fractal of dust, a chip of nitrogen ice, a hydrogen iceberg, a light sail. Each tried to square the lack of visible outgassing with the measured push. The lesson was not the final answer, but the method. Teams wrote down what thrust the path demanded, asked what natural sources could deliver it without lighting up the usual spectral bands, and kept score as models rose and fell. The headline for us is simple. Motion can reveal hidden forces, but motion alone rarely tells you the source. You need chemistry, rotation, and dust to pin it down. Then, 2I Borisov, the second confirmed interstellar object. A comfort to those who feared Oumuamua was a one-off trick. Borisov looked like home. It wore a classic coma. Its spectrum shouted water and carbon-bearing molecules that matched expectations. Its nucleus was small, and it behaved like a comet that had seen few warm seasons. The surprise there was not a new physics claim, but the realization that interstellar visitors could be boring in the best way. That case gives us a calibrator. When 3I Atlas leans away from Borisov-like behavior, carbon dioxide forward, water late, unusual tail geometry we know. The difference is not because interstellar equals exotic by default. It is because this particular object sketches a different chemical and dynamical childhood. Bring in Shoemaker-Levy 9, the comet that broke apart and dove into Jupiter in the mid-1990s. It is not interstellar, it is not an outlier in composition, but it teaches two crucial ideas. First, gravity and timing can turn a modest object into a global event. Tides shred, fragments line up, impacts paint dark scars visible from Earth. Second, prediction and observation can dance beautifully when the physics is clear. Observers knew when and where to look. The spectacle arrived on schedule. For our story, Shoemaker-Levy 9 is a reminder that the sky pays you back when you do the geometry homework. If 3I Atlas throws any sharp turns, the teams who built the outbound playbook will be the ones who get the decisive frames. Now, distill the rule. Natural until non-natural does not mean shrug until the spaceship lands. It means you write down the most conservative mechanisms that fit the data, quantify their limits, and push them until they break. If they hold, you learn something about nature's range. If they break in public with clean numbers, you earn the right to consider agency. The key word is earn. Every anomaly should face a ladder of natural explanations, sorted by plausibility and cost. Non-gravitational thrust from outgassing sits low on that ladder because we know it happens. Exotic materials that outgas invisibly sit higher because they require narrow conditions. Deliberate propulsion sits near the top because it changes the kind of universe we live in. Here is how those comparisons sharpen our eyes. Oumuamua tells us not to overtrust the absence of lines. You can have thrust without a bright chemical fingerprint if the gas species is awkward to detect, or if the production rate stays below a threshold. That means 3I Atlas must answer. Not only did the path change, but also, could the measured carbon dioxide, carbon monoxide, and water produce a push of the required size when mapped onto the known rotation? If yes, we do not need engines. If no, the ladder creaks. Borisov tells us that interstellar chemistry can be familiar, so differences at 3I Atlas carry more weight. A carbon-forward mix at long range that stays carbon-forward when heat rises nudges us away from typical comet playbooks and toward colder birth environments or stratified surfaces. If iron lines remain shy next to nickel across instruments, that is not a normal quirk we can wave away. It becomes a specific problem to solve with photochemistry, or with a source effect we have not modelled well. Either path is a discovery, a new regime of comet chemistry, or a signpost pointing somewhere stranger. Shoemaker-Levy 9 tells us to make predictions we can test with clocks. The reverse Oberth scenarios in our earlier chapter are not arm-waving if they end in times and angles. If someone draws a box in the sky and a week on the calendar and says a measurable deviation should accumulate here if a covert maneuver happened there, we can aim large telescopes with confidence. If the deviation does not appear, the scenario loses chips. If it does, the next stakes go up. That is how you use a spectacular, well-understood event from the past to demand rigor from a murky present. One more practical thread ties all three to our current visitor, the danger of narrative lock-in. With Oumuamua, early shape reconstructions painted a cigar. Later analyses favoured a flattened shard. The public memory barely updated because the first story felt cooler. With Borisov, many tuned out because it behaved, and we lost a chance to educate millions on why normal is wonderful. With Shoemaker-Levy 9, some forgot how much dull math powered the ore. For 3I Atlas, we guard against this by waiting later, better data, more than earlier, louder claims. We do not marry our first impression, we draft, put it in pencil. So if you need a pocket framework, as the re-emergence unfolds, carry this. From Oumuamua, track energy changes ruthlessly and be humble about invisible thrust. From Borisov, do not assume interstellar means exotic, measure how it is the same and how it is different. From Shoemaker-Levy 9, geometry pays dividends and predictions win the night. Add the rule that sits above them all. Keep everything natural, until natural breaks under numbers you can defend. Then, and only then, look up the ladder. Comparisons do not decide this story. They keep us from drifting. They remind us of the traps that past mysteries set for our attention, and of the disciplines that got us out. 3i Atlas will write its own curve. It will either bend into the familiar with some delicious quirks, or hold its angle stubbornly until we must admit that something more is at work. When we say natural until non-natural, what we really mean is this: reality first, romance later, if it survives the math. Could an object hide a message in flashes of light? Maybe. Could a noisy, rotating, outgassing comet fake a message so well that our eyes swear they see it? Absolutely. This is the knot we untie now. The claim on October 13th said, 3i Atlas, flashed in a pattern that maps to familiar Fibonacci numbers, 5, 8, 13. Here is how to catch a real pulse train, how to prove a fake, and how not to be hypnotized by a sequence our brains are already wired to love. Start with what a true optical pulse looks like. A pulse is a brief, repeatable uplift in brightness with rise and fall times that fit a physical emitter. In practice, you want millisecond-to-second cadence photometry with precise timestamps in coordinated universal time, calibrated dead time between exposures, and a sky reference to subtract atmospheric twinkle. You also want a rotation model in hand. The nucleus spins in about 16 hours. Any feature fixed to the surface will ride that clock. If a pulse train repeats at the same rotational phase night after night, you are likely watching a lighthouse effect from a jet or a specular flare, not a deliberate code. Noise is a trickster here. Atmosphere makes stars shimmer. Telescopes breathe heat. Tracking drives jitter. Cameras exhibit rolling shutter quirks, a non-linear response near saturation. Each of these can create spiky light curves that look like beats. The fix is redundancy. Observe the comet and a nearby comparison star with the same setup and cadence. If both show synchronous spikes, you measured the sky, not the comet. If only the comet spikes and the comparison stays flat, your signal survives a basic sanity check. Now, the math that breaks illusions. Do not eyeball. Run a period search across a wide range of trial spacings using tools that do not assume sine waves. Lomskargel is a classic for uneven data. Boxley squares is good for brief dips and rises. For pulse trains, use matched filtering with a short boxcar kernel to harvest energy in narrow bursts, then destroy the pattern on purpose. Shuffle the timestamps among the measured fluxes and rerun the search 1,000 times. That gives you a distribution of fake detections from noise alone. If your real detection does not exceed the 99.9 percentile of the shuffled runs, you have a pretty graph, not a pulse. Fibonacci invites a second trap. If you already expect 5, 8, and 13, your brain will round any near match until it fits. Guard against that by pre-registering thresholds. Decide in writing what tolerance around those intervals counts as a hit and what counts as a miss before you look. Decide how many misses turn the whole claim off. Decide how many trials you will run across nights before you stop fishing, then stick to that contract. The most honest result sometimes reads no pulses above threshold on these dates within this tolerance. That is not boring. That is clarity. There is also physics to respect. What could flash? Jets can flicker as vents rotate into and out of sunlight. Those are periodic with the spin and often asymmetric in shape. Dust clumps can glint if they have reflective facets. Those are usually short and rare. Electric discharge is sometimes invoked for drama, yet plasma in a tenuous coma would smear out at the scales we can resolve. Real optical beacons would require a compact source and a motive to spend energy. If you propose a beacon, you must explain why it rides a date, and a number yet ignores the elegant and cheap channel of radio where narrow band signals travel cleanly and timing is trivial to verify. That does not rule out light. It simply raises the bar. Timing hygiene matters as much as cadence. Use a clock disciplined by a global navigation satellite system or a network time protocol feed with logged offsets. Record the absolute start and end of each exposure, not only the midpoint, correct for shutter latency. Post raw frames and the code that extracts light curves, so anyone on Earth can rerun your pipeline and get the same spikes if they are there. A pulse claim without raw data and timing logs is a vibe. A pulse claim with both is an invitation to replicate. Spectral information can help, even with rough gear. If a flash is real and energetic, you might see a correlated blip in a specific emission band rather than a broadband uptick. A cyanide line that breathes with the pulse would argue for a jet. A featureless broadband flash could be glare from a rotating facet. A flash only in a narrow near-infrared slice might hint at thermal events. If no band shows a correlated change while white light spikes, you're likely chasing a processing artifact. Consider geometry too. As the comet re-emerges, phase angle and sky background change quickly. That can create false beats when automatic background subtraction lags the real gradient. To rule this out, measure the background in annuli that track the changing gradient and compare results. With multiple aperture sizes, real pulses will persist across reasonable choices. Background stumbles will not. There is one more clever cross-test. If a pulse train exists and is not locked to rotation, two observers far apart on Earth should record the same absolute timing within network clock error. If the train is spurious and driven by local seeing, the spikes will decohere between sites, organize paired sessions across continents, share ephemerides and cadence plans the day before. Publish both streams, aligned by precise time tags. That single figure can settle weeks of comment wars. What happens if you do everything right and see nothing? You win. A null result narrows the map. It tells you to hunt structure tied to rotation rather than to numerology. It tells you to spend telescope time on spectra and outbound astrometry, where the answer carries more weight. What happens if you do everything right and see a clean, repeatable rotation-independent train that survives, shuffles, cross-sites, and band checks? Then the conversation changes. You would have a physical effect that begs for a mechanism not covered by jets and dust alone. The burden shifts to explanation rather than detection. Could this all be a cosmic coincidence? Or is something else going on? That is the right mood. Curiosity with guardrails. The Fibonacci story is beautiful. Beauty is why we study the sky. Beauty is also why we must count carefully, blind to the story until the numbers insist. If 3i Atlas wants to talk in flashes, we will hear it. If not, we will have built a better ear for the next object that tries. When the lights go out at exactly the wrong moment, suspicion blooms by reflex. The Solar Dynamics Observatory takes a maintenance nap on the day the rumour spikes. The high-resolution Mars camera is offline through the prime window. A government shutdown furloughs people whose job is to turn raw ones and zeros into public pictures. Could this all be a cosmic coincidence, or is something else going on? Either way, outages are not just technical events, they are trust events. And trust, once dented, warps everything that follows unless we deliberately straighten it. Begin with how institutional pipelines actually work in space science. A spacecraft collects raw data packets. Those packets pass through calibration steps that correct for hot pixels, bias, dark current, flat field variations, pointing jitter, and cosmic ray hits. Teams then run higher-level product spectra with wavelength solutions, images with plate solves, light curves with error bars. Each stage has humans in the loop who check that an automated script did not quietly drift. When a shutdown pulls those humans, the pipeline slows even if the telescope is still happily watching the sky. That mundane explanation is real. It also does not erase the emotional optics when timing is bad. Now, flip the lens. From the public seat, space images feel instantaneous. We live in a world where your phone uploads a sunrise in seconds. A 3-week delay for a calibrated frame looks like Stone Age bureaucracy or intentional fog. The mismatch between professional cadence and public expectation is the fuel conspiracists burn. If you do not want that bonfire to spread, you do not lecture the public about patience. You redesign the pipeline for sunlight. Here is what sunlight looks like in practice. Publish observation plans before the event, with rough timelines for raw and reduced releases. When an outage is scheduled, post the dates prominently with a one-sentence purpose in plain language. If an outage is unplanned, post the incident report within 48 hours, even if the report simply says we are still diagnosing. When raw data are streaming but staff are furloughed, open a read-only bucket of raw frames with a disclaimer that says no calibration has been applied, download at your own risk. Citizen scientists and rival teams will make mistakes on those raws. That is fine. The cost of a few messy blog posts is far less than the cost of a vacuum that rumors rush to fill. Versioning matters too. When calibrated products arrive, stamp them with a visible version number and a changelog. If a flat field was wrong on Monday and fixed on Thursday, say so on the download page where a casual reader will see it. Hide nothing in PDFs. Use bullets and short words. This is not dumbing down. This is respect. There is a rhythm to updates that calms anxious ecosystems. Pick a daily or twice-weekly slot and stick to it. Even posting nothing new with a sentence that says no new releases today is better than silence. Silence is interpreted as choice, not circumstance. A A drumbeat, however small, restores the sense that competent adults are steering. The hardest piece is the "why should we believe you" zone when politics intrudes. Furloughs are not a lab's decision. Maintenance windows sometimes bow to vendor schedules and budgets, not science windows. Acknowledge that explicitly. Audiences can handle bad luck and bureaucracy. They cannot handle pretense. If you say routine when everyone sees the calendar weirdness, you invite eye rolls. If you say the timing is lousy and we know how this looks, you cut the legs out from under the loudest accusations. Let us talk about the other side of the handshake, the community that consumes. Transparency is a two-way street. If agencies post raws and timelines, the responsible response is to slow down hot takes and do cross-checks. Creators and commentators can build credibility by adopting a simple code. No cropped axes, no unlabeled units, no anonymous claims, and a mandatory link to the nearest upstream data page. Channels that follow that code should be amplified by platforms and peers. Channels that refuse should be called what they are: story shops, not science shops. Redundancy reduces drama. When the flagship is down, smaller instruments can fill parts of the gap. Ground-based, coronagraphs cannot replace a solar observatory, but they can watch flares and coronal mass ejections well enough to flag whether anything wild happened during the blackout. Small Mars orbiters cannot match a giant camera's resolution, but they can confirm presence, phase behavior, and rough photometry. A healthy ecosystem rehearses those backups in peacetime. When crisis hits, you already know who can spin up and what slice of the question they can answer. There is also a role for third-party escrow. Imagine a non-profit mirror that ingests public mission data in near real time and republishes them under its own uptime guarantees. Agencies retain authority for calibrated releases, but the mirror ensures that raw feeds do not disappear when a single server or policy does. This is not an insult to the missions, it is resilience. Oceans need buoys, science needs mirrors. Does any of this prove that nothing coordinated ever hides behind an outage? No. The world contains secrets. But building systems that default to candor shrinks the space in which bad faith can thrive. If, after all the timelines and raws and mirrors, a gap remains exactly where the story's hinge sits, the public will have earned the right to be suspicious, and professionals will have earned the obligation to investigate, not dismiss. Here is the trust equation in one line. Speed plus transparency minus defensiveness equals credibility. Space science wins hearts when it treats the public as partners who can handle caveats and incompleteness. It loses them when it mistakes polish for honesty. As 3i Atlas steps back into view, we will test not only comet physics, but also our institution's willingness to narrate in real time, to admit what they do not know yet, and to invite help from outside the badge. We cannot control coincidences. We can control how we behave when they stack up. Outages will happen again. A mission will blink at the worst hour. The choice in that moment is the difference between a rumor mill and a research community. Say what you know, say what you do not, show your work. Then watch how fast the temperature drops and how quickly the focus returns to the sky where it belongs. If numbers start leaning away from ordinary, if outbound speed is wrong by more than vents can pay, if the track bends the way only a deliberate push would bend, what then? We do not panic. We pick a tool. There are only 3 families of response in space: intercept, shadow, or wait. Intercept means go meet it fast. Shadow means park something along its path to watch for months. Wait means admit we are too slow this round and invest so the next visitor does not slip by while we argue on the internet. Each option has hard edges, but none are fantasy. Start with intercept. The romantic picture is a sleek probe knifing through the night, cameras hot, spectrometers thirsty, a hair's breadth flyby at kilometers per second. Reality is engineering math. Time of flight rules everything. If we detect a post-perihelion deviation in early December, the launch window for a chemical rocket sprint is measured in weeks, not months. That implies a ready-to-go bus small, robust, and built from parts already on shelves. Think CubeSat, class avionics, riding a kick stage that can deliver several kilometers per second of delta V, the change in velocity that turns a plan into a path. Navigation would be the real trick. An object on a newly bent course demands updates daily. That means a probe with cold gas or monopropellant thrusters for trim, a star tracker that can handle a dim field, and an optical navigation camera that can pick the target out of glare. You would accept a close pass rather than a rendezvous. At relative speeds of tens of kilometers per second, you get seconds of best data and minutes of useful approach and exit. That is enough to resolve shape to dozens of meters per pixel. to sniff the coma chemistry at short range, and to measure non-gravitational pushes from jets by watching the tail dynamics up close. Could we actually launch such a thing on short notice? Not from a cold start, no. But a standing rapid response stack is within reach. Pair a commercially available small launcher with an upper stage that can be stored fueled for months. Pre-integrate 2 or 3 probe buses with standardized instrument bays, a narrow-angle camera, a wide-angle context imager, a simple near-infrared spectrometer, a dust counter. Test them in peacetime. When a trigger threshold flips, say, an energy discrepancy that vents cannot explain you, roll the stack, upload a fresh trajectory, and light the candle. The risk is high. The payoff is disproportionate. Even a failed flyby that misses by a few hundred kilometers would produce navigation images and engineering lessons that make the next sprint smarter. Shadow is the quieter cousin. Instead of a dash, you put a sentinel in a heliocentric orbit that naturally crosses the lanes interstellar objects favor. A solar sail or an efficient electric propulsion craft could loiter on the outskirts and spiral inward or outward to match targets of opportunity. It carries modest instruments and a beefy antenna. It does not need planetary gravity assists. Its currency is patience. When alerts go out that a new object is inbound or that an outbound object is acting strange, the Sentinel tacks and trims to place itself thousands of kilometers off the target's path weeks in advance. Shadow missions trade immediacy for certainty. You watch longer. You measure variability over rotations. You catch outbursts without the pressure of a 1-second closest approach. Waiting, done correctly, is not doing nothing. It is building a pipeline so good that we stop having this conversation about missed chances. The core pieces are clear. Understanding rapid astrometry network with automatic handoffs around the world, so positions never go stale for more than an hour. Equip a dozen mid-sized observatories with identical low-resolution spectrographs and a shared reduction pipeline so nightly chemistry baselines publish themselves. Support a public dynamics server that ingests those positions and spectra and spits out an updated family of possible paths with gas thrust estimates everyone can see. And crucially, design, qualify, and store a ready-to-fly probe bus as national or international infrastructure, not as a bespoke one-off. What would a successful intercept or shadow actually tell us that ground and space telescopes cannot? 3 things: structure, texture, and context. Structure means geometry at scales that lock models. A nucleus with facets and planes is a different animal from a lumpy snowball. Texture means albedo changes and thermal behavior across that geometry, dark seams that drink sunlight, bright scars that vent. Context means how jets couple to motion in real time rather than inferred from distant light curves. If a maneuver happened, a close pass could catch residual plumes, heat signatures, or debris fields in the act. If nothing happened and the object is simply weird, a close pass would pin down which kind of weird to teach in textbooks. Risk lives everywhere in these plans. Launch on short notice has higher failure odds. Close passes at high speed can blind instruments or yield motion blur if your tracking is off by fractions of a degree. A sentinel can spend years waiting and miss the one object everyone cares about. Waiting can harden into inertia. The antidote is portfolio thinking. Do not bet everything on one probe, one sail, one dashboard. Spread the bets and set clear triggers for when each tool moves. Here is a concrete trigger sheet. If the outbound energy differs from inbound, beyond the 99% envelope of natural non-gravitational fits, greenlight a sprint probe if a stack exists. If repeated, rotation-independent optical pulses are confirmed by 2 sites and survive time shuffle tests. Prioritize a sentinel retarget to watch continuously for a month. If neither occurs and the object behaves within stretched but normal comet physics, double down on the wait plan. Publish the best interstellar comet dataset in history and pour that credibility into funding the rapid stack so the next one does not get away. Is any of this cheap? Compared to a flagship mission, yes. Compared to doing nothing and arguing forever, absolutely. A rapid sprint stack could live under the budget of a small planetary mission if built from commercial parts and a short instrument menu. A Sentinel with electric propulsion and a modest payload could be a shared international asset with slots for partner instruments. The dashboard and network pieces are cheapest of all and can be run by a lean non-profit with agency partners. Could this all be a cosmic coincidence, or is something else going on? That question should light a practical fire, not just an imaginative one. The choice to intercept, to shadow, or to wait is a choice about who we want to be as a species when the universe knocks and then starts to walk away. Curious is good, prepared is better. Prepared and humble is best. Build the stack, fly the sentinel, keep the dashboard honest. And when the next interstellar visitor appears, or when this one surprises us again, we will have traded helpless wonder for informed awe. The glare fades, the first positions land. Now what? Rather than cling to a single story, we build a decision tree and let the sky walk us down its branches. Clear branches help everyone keep their head. They also keep us honest. If the data point here, we go there. If not, we take the other path. No drama, just choices backed by numbers. Branch 1. Nothing unusual. The outbound speed matches the inbound energy within the envelope that normal outgassing can explain. The trajectory is a clean mirror with the small, smooth nudges you would expect from heated vents. Spectra evolve gently. Water strengthens as fresh terrain warms. Carbon dioxide stays present, but stops being the star of the show. The nickel lines soften or iron appears as sensitivity improves. The rotation clock keeps time and the light curve patterns lock to that drum. In this branch, the headline is Quiet Confidence. 3i Atlas becomes the most carefully studied interstellar comet to date, with a personality that expands our catalogue rather than breaks it. The takeaways are still rich. Cold formation looks likely. Layered surfaces look common in the galaxy. Early inactivity, followed by a rapid wake-up, becomes a model you teach. The public may sigh. Scientists smile, publish, and use the goodwill to fund the rapid response stack so we can do even better next time. Branch 2. Unusual but natural. Outbound energy is off by a hair, yet within reach for jets if you push every knob to the edge. The path bends a little more than expected. The brightness does a small step that lines up with rotation and a likely vent. Spectra show nickel staying loud, while iron mostly hides across several instruments. Cyanide scale lengths change with season and geometry in ways models can accommodate with effort. The dust map confirms a sunward-leaning feature that curves back the way radiation pressure predicts if grains launch fast and heavy. In this branch, we learn something fresh about comet physics in a high-carbon regime. Photochemistry in carbon monoxide-rich gas turns out to be more dramatic than textbooks said. Jet efficiency near perihelion gets an update. The message to the world is humble and exciting. Nature had more tricks up its sleeve than we remembered. No engines required. Branch 3. The red flag. Outbound energy is lower than any reasonable gas thrust budget can cover, even with optimistic dust to gas drag. The new best fit track refuses to reconcile with standard non-gravitational terms tied to rotation. The deviation grows across the first 2 weeks rather than shrinking. Spectra do not show the gas surge that would pay for the measured shove. Independent teams, using different pipelines, converge on the same arithmetic. In this branch, you activate the intercept or sentinel plans from the last chapter. You do it without panic and with a tight public rationale. The wording matters. We do not claim artificiality. We claim a mechanical discrepancy that deserves hardware. The next moves are checklists, not vibes. Short window radar if geometry allows. High cadence tracking to tighten the post-blackout family of paths. Rapid calls to observatories for continuous coverage. And if a sprint probe stack exists, a formal go or no-go review within days. Branch 4. The strange communicator. Repeated, rotation-independent optical pulses show up and survive all the tests that kill pareidolia. 2 sites on different continents record the same absolute timing within clock error. Spectral bands pulse in sync in a way that cannot be blamed on seeing or processing. No one expects this branch, which makes it the one that will cause the most fuss if it appears. The correct response is not to assign intent. It is to map the pattern and watch how it evolves. You publish raw and reduced data in real time. You invite radio and X-ray observers to stare at the same windows. You ask whether any nearby spacecraft saw coincident particle changes. You treat it like a physical phenomenon first. Later, when the count is secure, you talk about possible meanings. If the pulses ride numerology that the public recognizes, you acknowledge that without letting it drive the bus. We can also add a small fork that sits across all branches, the holiday geometry. On late December dates, the object sits at a dramatic angle relative to Earth that human culture is filled with stories. It will be tempting to narrate meaning onto that alignment. Resist. If the physics in early December is ho-hum, late December will be ho-hum with nicer lighting. If the physics in early December is wild, the late December will still be wild, only more people will be watching. The calendar is not the engine is the engine. What about risk to Earth? This tree keeps that answer in the same place it has always lived. Risk is a matter of path and speed, not of headlines. If the post-blackout track threads anywhere near our lane in the coming months, that will be clear in the nightly updates long before any approach. If the track stays wide, The only thing crossing your sky will be photons and theories. The comfort is that both outcomes are visible to amateurs and professionals alike. The path cannot be hidden if many eyes look. How do we communicate while walking the branches? With checklists and dashboards, each day you update 4 plots. Position residuals against the inbound mirror. Brightness residuals against the inbound model, adjusted for distance and phase. Rotation folded light curves for the clearest bands. Spectral band strengths for carbon dioxide, water, cyanide, nickel, and iron. Each plot carries a green, yellow, or red band for natural, strained natural, or discrepant. You post a 1-paragraph note that says exactly where the point landed and what that means for the tree. If the dot crosses a line, you say what trigger fires next. This is how you keep the story from being captured by the loudest voice in the room. There is also a human branch that matters. People will feel whiplash if the tree turns sharply. Plan for it. If the outcome is quiet, celebrate the win without mocking those who hoped for fireworks. Curiosity is not a crime. If the outcome is loud, temper the thrill with care for those who will be scared. Frameworks that shrink fear are simple. Explain what is known, what is unknown, and what is being done. Replace speculation with watch items. Keep timelines concrete. Tell people what to look for in tonight's sky plots and when to expect the next change. Most of all, write down now what will count as a pivot. If outbound energy misses the natural envelope by this amount, we turn right. If iron appears above this strength, we turn left. If pulses do not replicate across sites by this date, we prune that branch. Pre-committing protects us from moving goalposts under emotional wind. The tree is a promise to our better selves. Could this all be a cosmic coincidence, or is something else going on? The tree does not care. It only cares where the next dot falls. In a few nights, the shape will become obvious. In a few weeks, the branch will be chosen. And in a few months, we will either file 3i Atlas under the most instructive comet of the decade, or we will pin a new page to the wall labeled something we did not expect and were ready to study anyway. That is the whole point of a decision tree. You prepare for wonder in both directions. Let us do the uncomfortable thought experiment cleanly. Suppose the outbound numbers refuse to fit, and the simplest natural ladders snap. Suppose a repeated rotation-independent signal survives every null test, or a measurable energy change appears where no jet can pay the bill. Then 3i Atlas is not just geology and sunlight. What happens next should not be left to adrenaline or to the loudest live stream. There are boring, humane, scientifically honest steps that make the difference between panic theatre and grown-up curiosity. Move 1. Freeze the narrative and flood the data. That means immediate, mirrored posting of raw and reduced observations from multiple teams, with synchronized clocks and minimal commentary. When reality is surprising, the best antidote to rumor is oversharing the measurements with enough context that others can replicate. Short sentences, clear plots, and public code. No metaphors. No music, just the numbers anyone can check. Move 2. Convene a cross-discipline room, not a secret panel. A visible, time-limited task group with names, organizations, and a mandate. You want astronomers, spectroscopists, information, theorists, radio engineers, spacecraft operators, signal processing hawks, risk communicators, and a few people whose job is to say, we might be fooling ourselves. Their charter is simple. Define the minimum further tests that could turn a staggering claim into a sturdy one, or bury it without drama. Publish the checklist and the timeline. Move 3. Treat communication as public health. Fear spreads on the same channels as facts. The messaging cadence matters. Daily briefings with 3 pieces. What we measured, what we do not know, what we will try next. You cannot promise certainty. You can promise clarity and humility. Visual dashboards beat talk shows. When mistakes happen, pin the corrections at the top of the same channels that carried the earlier posts. Trust goes up when institutions admit error in daylight. Move 4. Run the compatibility tests. If an apparent signal exists, try to detect it across the spectrum. Optical, radio, infrared, maybe X-ray, if physics suggests it. Check polarization. Check for dispersion that would mark a path through plasma. Check whether the timing survives barycentric corrections that account for Earth's motion. Try to decode only after you have locked down that it is not an artifact of instruments, atmosphere, or human bias masquerading as mathematics. Declare null results loudly. Declare positive results with probabilities and caveats attached like price tags. Move 5. Separate detection from meaning. The human urge to interpret will be volcanic. Resist it. A repeating pattern does not make a greeting. An energy change does not make intent. Your first and second jobs are characterizing a phenomenon and ruling out our own systems as the source. If meaning eventually enters the room, it should arrive trailing a bibliography, not vibes. Move 6. Activate the non-confrontation rule. If an object looks capable of maneuver and is on a path that could intersect ours, the correct posture is strictly observational. No lasers, no. Radar pings unless geometry and prudence say, risk is negligible. No attempts to alter its state. Curiosity does not require poking. If it is a probe under someone's control, uninvited interference would be childish and potentially dangerous. We listen and watch. We do not touch. Move 7. Call the right diplomats, not the wrong generals. Any legitimate government alert should route through science and disaster communication channels first, with pre-agreed language that avoids threat rhetoric, unless and until a path or behavior demonstrates risk. The world has committees for planetary defense and near-Earth objects. Use them. Expand the table to include ethicists and interfaith leaders early, not to bless anything, but to prepare communities for uncertainty without inflaming them. Move 8. Decide whether to respond and how. If a signal looks intentional and decodable, the messaging to extraterrestrial intelligence debate becomes real rather than academic noise. The safe principle is easy to say and hard to practice. Do not answer in haste. The planet deserves a deliberative process with global input before anyone transmits from a big dish. Meanwhile, laboratories can test hypothetical responses locally by bouncing them off the moon or beaming them to nowhere to check for unintended consequences. Listening is free, speaking is not. Move 9. Protect the vulnerable. Big ideas bend minds. Some people will experience acute anxiety or existential grief. Others will be targeted by grifters selling apocalypse kits or cosmic salvation. Public health systems and platforms should prepare now for a wave of disinformation and for a need in counseling services that is measured in weeks, not hours. Education helps here. So does compassion. Remind people that new knowledge rarely changes daily life overnight. Food still cooks. Children still need bedtime stories. The sky being more interesting than we thought does not cancel bills or friendships. Move 10. Keep science. Weird and rigorous at the same time. Announce prizes for replication and for elegant refutations. Fund instruments quickly to chase the phenomenon without starving ongoing research. Expect academic turf wars. Interrupt them with open data and with credit sharing that rewards cooperation. The goal is not to crown a hero. It is to map reality faster than rumor can. If you must pick a slogan, pick measure twice, talk once. Answers to the hard questions remain the same under pressure. What is it doing? Where is it going? How is it changing energy? What is the light made of? Do independent instruments see the same thing? Every time speculation starts to bloom into fan fiction, return to those 5. If the phenomenon keeps behaving like physics plus intention, the evidence will continue to stack in plain view. If it relents into dust and jets, the extraordinary will collapse back into the merely fascinating. Either way, having a playbook beats improvising in front of 8 billion people. Could this all be a cosmic coincidence, or is something else going on? That question got us to look harder. The next questions are gentler and wiser. What is the next measurement that matters? Who else can make it? How do we show the world the result without drama? If we can do that for a month, the story writes itself. If we can do it for a year, the culture grows up a little. And if we can do it every time the universe nudges us with something strange, we will deserve whatever answers we get. When the excitement cools and the dashboard stops swinging, we are left with a quieter question that matters more than any single plot. What do we change so the next interstellar visitor does not depend on luck, rumors, and midnight heroics? Curiosity got us here. Capability gets us farther. The path from wonder to systems looks unglamorous at first glance. Networks, standards, boring names like latency and uptime. Yet this is how civilizations level up. You turn what was once an emergency into a Tuesday. Begin with eyes. The sky is large and our attention is small. We need a permanent discovery engine that finds travelers early, not weeks before perihelion. That means more wide-field surveys stitched into a single rolling net. A telescope in Chile sweeps the southern sky tonight. A twin in the north picks up the baton before dawn. A smaller robot in Namibia fills the gap. Their images stream into a shared queue where asteroids, comets, and artifacts are triaged by the same open code. False positives are not a nuisance in this world. They are the tuition we pay for speed. The prize is 6 months of warning instead of 6 weeks. Next, keep time like grown-ups. Every small observatory that wants to play in the fast lane should have a disciplined clock and a posted time offset log the way ships post weather. Do not count on computer defaults. Use a satellite-disciplined reference or an audited network time feed, and bake the timing metadata into each image header. A pulse claim without hard time is a ghost. A path deviation without millisecond stamps is a shrug. The fix is not expensive. It is culture. Spectra should be as common as pretty pictures. Equip a dozen mid-sized observatories on 3 continents with identical low-resolution spectrographs and a shared reduction pipeline. Run drills in peacetime, where all of them observe the same bright comet and publish within a day. You do not just test the optics. You test the humans, the upload scripts, the emergency contact lists. The first time you learn that a spectrograph hates humidity or a mountain network dies in a storm should not be the night the internet is melting down over a rumor. Turn amateurs into a standing army. The most agile observers on Earth are the ones who can set an alarm at 3 in the morning and change plans at 4. They already own good gear. What they lack are coordinated playbooks and small grants for upgrades that matter. Fun-time discipline kits, narrowband, filters tuned to key comet species, and cloud storage credits. Write simple play cards in plain language. If you see this, do that. If you cannot, hand off to this person. You are not just buying data, you are buying resilience against outages and against slow official releases. Build mirrors. Raw space mission data should flow to more than one public server with different administrators, different power grids, and different incentives. One can be agency-hosted. A second can be a university consortium. A third can be a non-profit whose only job is uptime. When a maintenance window hits or a budget fight freezes a pipeline, the mirror keeps humming. Mirrors do not solve politics. They make politics less able to slow physics. Standardize the 4 plots that stopped 1,000 arguments this season. Position residuals against a published inbound mirror. Brightness residuals against a distance and phase model. Rotation folded light curves. Spectral band strengths for the handful of molecules that matter. The trick is not artistry. It is sameness. If everyone posts different axes and different units, the public has no chance. If everyone posts the same 4 in the same order with the same units, a teenager learning at home can keep up and spot nonsense from a mile away. Now, hardware. Stop imagining bespoke heroes launched in a panic and start imagining shelves. A standing sprint stack is not a fantasy. It looks like this: a small launcher on retainer, a storable upper stage fueled and checked monthly, 2 probe buses built and parked, each with a narrow-angle camera, a wide context imager, a near-infrared spectrometer, a dust counter, and simple thrusters for trim. Paperwork done. Insurance in place. When the trigger flips an energy discrepancy outside the natural envelope, or a replicated rotation-independent signal, you roll, upload, and go. If nothing flips in a year, you exercise the stack on a safer target and call it training. Add a patient cousin in deep space. A solar sail or efficient electric propulsion craft already in a heliocentric orbit, ready to shadow. Its job is boring and therefore vital. Drift, wait, trim, watch. The payoff comes the year a visitor arrives on a path the sprint cannot catch, or when we need months of context rather than seconds of close-pass drama. Agencies can build one. So can a coalition of space clubs if you give them access to a mid-range dish and a sliver of deep space network time. Ambition is welcome. Modesty is powerful. Education is the multiplier. Replace the folklore that science equals certainty with a cleaner mantra. Science is measurement, plus humility, plus iteration. Put that on classroom walls. Run student exercises with real interstellar data, where the homework is to replicate a light curve and decide whether the deviation is noise or news. Host public nights where you show how to fold a light curve on a 16-hour period and watch vents paint the sky. You will not stop every viral rumor. You will shrink the pool it can swim in. Finally, write the social contract in daylight. Agencies promise raw releases on a clock, version products with changelogs, and the courage to say the timing is bad, and we know how this looks. Creators promise to link sources, label axes, and publish code for any strong claim. Platforms promise to boost primary data threads from missions and consortia when a story spikes, not just the loudest thumbnails. Audiences promise to reward correction as much as revelation. None of this requires a law. It requires taste. Could this all be a cosmic coincidence? Or is something else going on? The honest answer is that the universe will keep throwing curveballs whether or not we are ready. Readiness is our part of the story. It is a choice we can make on ordinary Tuesdays with budgets, checklists, and drills that feel unromantic until the night they save everyone time and dignity. The next visitor is already inbound from somewhere. If 3i Atlas taught us anything, it is that awe grows when it meets method. Build the method now, then let awe do what it does best. When a story like this crests, something quieter begins. The feeds slow, the graphs stop jerking. You take a walk at night and notice the old sky again, familiar stars holding their silent quorum. Whatever 3i Atlas ultimately proves to be, we still live under the same darkness that has always held room for imagination and for math. Our job now is to carry forward the best parts of what the last months woke up in us, and leave behind the reflexes that made us noisy, tribal, and tired. First, let us talk about wonder without panic. Curiosity is a survival trait. Panic is a short circuit. One keeps you scanning horizons, the other shrinks your world to the size of your fear. The difference is practice. You practice it by returning to questions you can answer tonight. What did we measure? What changed? What stays unknown? You do that in public with plots and plain words. You do it at home by teaching your kids to ask for sources, to label axes, to say I do not know yet with the same pride they feel when they ace an exam. Wonder grows when it is paired with competence. Panic withers in the face of steady work. Meaning without myth is the next trick. Humans are pattern makers. We wrap numbers in stories because stories travel faster than tables. That is fine until the story hardens around a claim the numbers cannot carry. Then myth calcifies where meaning should breathe. The fix is not to ban stories, it is to keep them provisional. You can say this feels like a message, and still commit to the test that would keep it from being a mirage. You can say the date feels charged, and still admit that calendars are human furniture, not cosmic engines. If the phenomenon keeps passing the tests, meaning will ripen. If it fails, the story can set it down gently and walk away. Community matters more than any single plotline. This season organized strangers into a distributed lab. Amateurs in backyards handed their night to professionals on mountaintops. Coders wrote tools that teachers turned into lessons. That braid should not unravel just because the glare has passed. Keep the listservs alive. Keep the open repositories warm. Turn the playbooks into public guides for the next object, the next eclipse, the next bright comet your neighbor will ask about over the fence. A culture that shares work is harder to fool and easier to steady when rumors spike. We should also name what hurt. Outrage algorithms rewarded the most breathless takes. A few actors treated speculation like a product. Institutions sometimes mistook good optics for good faith. You felt it every time a confident voice asked for your trust without receipts. The antidote is not cynicism. It is taste. Reward sources that show their homework. Reward creators who correct themselves in daylight. Reward agencies that post raw files on a clock and admit bad timing before anyone asks. Starve the rest. Attention is a currency. Spend it on people who treat reality like a common asset, not a stage. What about faith? Philosophy? The human ache for meaning bigger than a spectrum line. They belong here too. Not as trump cards, but as companions. If the universe is louder than we thought, some will feel small, others will feel accompanied. Either way, communities need rituals for uncertainty. A night where you walk out and look up together is not childish, it is medicine. A classroom exercise where students fold a light curve and see a 16-hour breath written in photons is not just science. It is a lesson in patience. A poem about a comet that might be a machine is not a distraction. It is a way to hold the question without rushing to an answer. Education is the lever we can actually pull. Replace the myth that science equals certainty with science as a posture. Measure, doubt, revise. Give students raw interstellar data and let them argue kindly about whether a bump is noise or news. Teach the phrase, strong claim, weak evidence, and how to live inside that tension without reaching for slogans. Teach the difference between a model that fits and a model that explains. Do that enough times, and a rumor wave becomes a learning moment rather than a stampede. There is also the matter of dignity. People came to this story carrying different temperaments. Some wanted awe, some wanted proof, some wanted comfort. You probably saw all of that inside yourself across different nights. That does not make you inconsistent. It makes you human. The path forward honors both the kid who still hopes for a message from the dark and the adult who knows how hard it is to catch even a clean spectrum. The internet often punishes nuance. Real life rewards it. Keep your nuance. If 3i Atlas fades into the ledger as a complicated natural traveler, we still won. It pushed our instruments, our pipelines, our patience. It gave us a rehearsal for the day. Something genuinely new asks us to grow up fast. If 3i Atlas keeps a sliver of mystery alive even after the data settle, we still won. Not because we can smuggle any story we like into that sliver, but because we learned how to stand near wonder without making it smaller than it is. In the end, the sky is where we practice being a better species. Night after night, it asks for our attention and our humility. It lets us be wrong without punishment beyond embarrassment. It rewards care. It refuses to conform to our schedules. It invites collaboration because no single scope or person can hold it all. That is not just astronomy. That is a rehearsal for every crisis, discovery, and conversation we will have together down here. So take one last look at the quiet dome above you. Think about the teams who built mirrors and code. Think about the parents who woke their kids before dawn to see a tiny smudge move against the stars. Think about the patient plots, the blunt corrections, the carefully worded updates that kept a billion hearts from jumping too fast. Then carry that posture back into your ordinary days. Count carefully, share generously, hold your stories lightly. And when the next visitor comes humming in from the dark, meet it with the same mix of method and awe that made this season worth the lost sleep.